Aprajit Mahajan. I am a development economist. I teach at UC Berkeley. I also have done some work in econometrics, and so most of my lectures today will kind of reflect a combination of both of those. I'll present mostly results from a few papers, and I'll try to, rather than give you kind of a broad overview of a field, I'll try and sort of give you more details of a particular set of papers, mostly because I think when I talked to Sandeep, he told me most people here are PhD students, and so I figured this might be a better way to generate ideas for dissertations rather than give you like a overview of a particular field or a topic. So the first lecture is going to kind of try and do two things. So first is I'm going to try and introduce you to kind of what are the various advantages and disadvantages of using randomized control trials and structural models in economic work. So I think you've had Gaurav and Namrata and Lakshmi all talk to you in the past 3 days, and I think they've all talked about some aspects of at least randomized control trials to you already. So you have a pretty good sense of what those are. So this will mostly be just a review and just to set the stage for thinking about structural models. And what I'm going to do mostly is walk you through a couple of papers that I think try and combine both of these approaches to address a given topic. So I think that traditionally people think of these as being kind of different approaches to answering a question. And what I want to show you today is that in fact they can usefully be used together to answer the same question. So that's kind of the overall message of this lecture, sort of how to think about using randomized control trials, or more generally some source of exogenous variation that you introduce as the economist to identify a particular model that you are interested in. So that's sort of the agenda for today. And the particular structural model that I'm going to use is going to be a very standard kind of model that you should have seen hopefully in your first year or maybe in your second year. These are these dynamic discrete choice models. So they're a kind of workhorse model for applied empirical work. If you've taken industrial organization, this is a standard tool to study any kind of intertemporal choice problem. In first year macro, you probably saw Euler equations and things like that that are kind of dynamic choice in the context of continuous choices, right? So if people are choosing consumption, that's continuously, and so that's a continuous variable, and so solving that dynamic choice problem gives you an Euler equation. Here the difference is going to be people are making a discrete choice. So in each period people have to make one of three choices. Either you do something or you don't do it, or in the particular example I'm going to use, how many tasks are you going to complete in a particular period. So that's sort of why why I'm thinking about dynamic discrete choice. But the underlying idea is the same as you should, going back to your first year macro kind of sequence. So thinking about just giving you kind of a one slide introduction to thinking about causality in economics. So this has a very long history, going back at least to 1953, but also before that there's versions of this. And so kind of the one way to think about this literature is to sort of say that the Coles Commission, starting with Koopmans in 1953, thought about causality within the context of kind of simultaneous equation models, right? So these 10 years ago, 15 years ago, these used to be a standard part of the first year econometrics course. When you did OLS, IV, you would also do a section on simultaneous equations, right? And so this idea was that you had, 3 endogenous variables, 10 exogenous variables, and you would write down 3 equations that would explain each of these 3 endogenous variables as a function of the exogenous variables. And the idea was that these fully captured all of the causal relationships in the world you were trying to study. Okay, so that was kind of the approach that the Coles Commission took. And so this was all typically in the context of linear simultaneous equation models. So all of these equations were linear, and then over the course of the next 20 to 30 years, kind of a very well-developed theory of trying to identify and estimate these systems of simultaneous equations was developed within econometrics and with applications in a range of fields, including macro, as well as kind of more econometric methods. So starting in kind of the late 70s, particularly in macro, the approach to causality became a little bit more, if you like, theoretical. So the most famous paper here is Sim's paper from 1980, in which kind of causality was defined in the context of what's called Granger Causality, which is kind of a temporal notion of causality, which in some sense is much more ad hoc than kind of the notion of causality that we think about in terms of the simultaneous equation models, and also relative to the kind of notion of causality that I'll be talking about today. Within applied microeconomics, which is kind of my field of interest, the notion of causality has been around for a long time, and people have used different approaches to think about it. One way to think about it is to think about kind of the first formalization of this notion. So the first formalization of this notion that you can trace back to Jerzy Neyman, who was a statistician, who introduced this notation of potential outcomes, which was kind of this key formal kind of underpinning to thinking about causality. And so how many of you have seen this kind of potential outcome notation before? So, okay, so I'll spend some time introducing this potential outcome notation, but you can think of this as kind of a very basic way to think about causality. There's been numerous debates, especially within statistics, about how useful it is as a way of thinking about causality, and within economics as well, there's been lots of debates between how useful this way of thinking about causality is versus kind of the more standard way economics has of thinking about causality, which is, which goes back to the Coles Commission, but you've probably seen it in your first year sequence if you've seen kind of these Heckman selection models, or if you've seen Roy models, which are also kind of models based on discrete choice, right? So in both of those, so one way to think about it is to think about these Heckman selection models or these Roy models as being the econometric analog of this Jerzy Neyman's kind of potential outcome notation. And in a famous paper in 2002, in fact, one of Jim Heckman's students at Whittlesey kind of showed that these are equivalent. So right, he showed that if you write down kind of a Roy model of sample selection or a Roy model of occupation choice and this Neyman model, these models actually are in fact equivalent to each other. So really, the way in which we should think about causality, you can think about it using the Neyman framework, you can think about it using this kind of Heckman style framework, and suitably generalized, they're both kind of equivalent to each other. Within this push towards randomized controlled trials in development, people have tended to use this Neyman notation more than kind of this traditional econometric notation. And that's partly because this literature on randomized controlled trials historically has used this kind of Neyman notation to try and understand causality. But if you are more used to thinking about it using these, using kind of standard econometric models, you can think about this in terms of those as well. Okay, so I'll talk a little bit more about what I mean by that when I introduce the Neyman potential outcome notation. So that's kind of the formalization, but thinking about how people have used it, I want to go back and talk a little bit about this idea of using natural experiments, which is kind of a precursor to randomized controlled trials, or at least the growth of randomized controlled trials in economics. And so this is the idea that you sort of use some kind of exogenous variation that already exists in your observational data, and you use that kind of exogenous variation to try and answer a question of interest, right? So this has a long history. Most people actually trace this history back to this work by John Snow, who proved using essentially a natural experiment that cholera was a waterborne disease, right? So I don't know how many of you have heard this story before. So not many. So this story was basically, so John Snow was a medical doctor in England in the 1840s, and in London, especially during this period, especially during the Industrial Revolution, when you started to have dense populations living together, you started to get these epidemics of cholera. But during that time, there was no scientific explanation for what caused cholera. In fact, a scientific explanation would not exist until the 1870s, when a German scientist actually discovered when the germ theory of disease became prominent and the cause for cholera was discovered. But in 1840, John Snow, who was a doctor, kind of tried to understand what caused cholera. And his hypothesis was that this was actually a waterborne disease. And this was actually fairly controversial at that time because, existing theories posited by, eminent scientists at the time had a range of explanations. It was bad air, it was this, or it was that. And so what essentially John Snow did, if you think about it in modern econometric terms, is basically he ran a reduced form regression, or he did a kind of reduced form analysis. But what he did in terms of collecting data was to look at mortality rates from cholera at different locations in London. And in particular, what he noted was that different neighborhoods in London received their water from different points along the Thames River. Now, of course, in London in the 1840s, it was also the case that all of the kind of waste matter was also disposed into the Thames. So both the drinking water was obtained from the Thames and all the wastewater was kind of disposed into the Thames. And what he noticed was that there were some neighborhoods that would get their drinking water at a location just below a point where a sewer pipe basically emptied all of the waste into the river. And there were some neighborhoods that received their water from a point that was above these locations of these sewer pipes. And so he divided neighborhoods into two types: types that received their water just above the sewer disposal and types that received their water from just below the sewer disposal. And he compared mortality rates between these two kinds of neighborhoods, right? So this is a very kind of, if you think about it now, it's a fairly standard or simple kind of exercise. At that point, it was, it took a lot of insight to kind of figure out that if it's waterborne, how might you test the hypothesis that it is waterborne? And then you try to find out, or, what he basically did was he found what he thought was a natural, what we would, in our terminology, think of as a natural experiment. And the experiment would be that the way these pipes were allocated in how they flowed into the Thames and how the drinking water was drawn was essentially random in some sense. It wasn't necessarily connected to how wealthy the neighborhood was, for example, which might be one confound. And he showed, in fact, that mortality rates were much lower in the areas that drew their drinking water from above the point where the sewer discharged into the river. And so that was kind of his argument for why cholera was a waterborne disease. And he also did what we would, in contemporary kind of econometrics, think of as kind of robustness checks. So he compared neighborhoods that drew their water from just below and just above the sewer disposal, and he showed on a range of kind of variables that these were quite similar to each other, in terms of population densities and so forth. So this was kind of the first, histories of natural experiments or histories of instrumental variables will typically cite this study, which is often just called Snow on Cholera, as kind of the first example of using natural experiments to study a question of interest. And he wasn't entirely successful in convincing people that it was waterborne, but there was certainly a widespread, at least a certain, a substantial number of people were convinced by this kind of study. And so over time, there have been many versions of these kinds of studies that have been trying to use some source of exogenous variation. I think within economics, trying to use these kind of natural experiments as a source of exogenous variation really started, I would say, sometime in the early 90s might be one way to date it. And again, the idea here was to try and use different kinds of exogenous variation, largely in non-experimental data, to answer a question of interest. So those of you who've taken labor economics, which in the US basically means just data sets that use US data. Angrist and Kruger have a set of papers that use different kinds of exogenous variation, whether it is kind of the draft lottery for the Vietnam War, or whether it's the quarter in which you're born, to try and understand things like the return to education, right? So that's one way of thinking about causality. And so you might ask, kind of, these look like different methods of trying to understand causal mechanisms. Is there kind of a story behind why certain methods became popular when they became popular? One way to think about the development of these methods is to think about them kind of being developed for different kinds of data. So one way to think about this whole, the Coles Commission and the Granger Causality approaches as being trying to put a lot of structure on pretty limited data. So you can think of economics from the 50s to the 80s as basically being a situation where you had relatively little data. And so what you did was to put a lot of structure in order to interpret that data in a reasonable way, right? So you can think of this period as being one where you put a lot of emphasis on theory and on structural modeling to try and interpret the data. And you can think of kind of the work from the mid-80s onwards as being one that's really trying to look at causality by trying to look for better data. Okay, so you can think of that as being these natural experiments. You go out into the world, you try and see, what kind of data can I find to answer this question that I'm interested in, right? So one way to think about this is from the 80s onwards, there's really been kind of this approach towards trying to find better data to answer the question you're interested in. And you can think of randomized experiments as being just one approach to finding better data. Then you kind of create your own data, right? You go out and run an experiment and you create your own data. Of course, that's a very expensive thing to do. It takes a lot of money to run an experiment. And so it's not always possible to create your own data, but there might be natural experiments that exist that give you variation that is similar to that would be generated by a randomized controlled trial. So that's one way to think about this distinction, kind of, putting a lot of structure on limited data versus getting better data. But one way to think about this lecture today is to kind of say, well, you can do that even you can sort of combine the two approaches, right? You can go out and collect your own data or look for better data, but combine that by putting more structure on that data as well, right? So you can think about a world in which you have better data, but you're also putting more structure on that data because maybe you're getting more ambitious in the kinds of question you want to answer as well. Okay, so that's one way to think about this lecture, is to sort of say, now we have better data, but let's also try and put more structure so that we can extract even more from this data. Okay. So since this in particular, this is kind of a course on development economics, I'm going to focus on the approach towards better data and better analysis within development. And within development, the big story over the past 20 years really has been this kind of huge growth in the running of randomized controlled trials in a lot of different parts of the world to answer questions of interest, right? So this is extremely popular. So let's just do a brief overview about randomized experiments and kind of talk about the things that they're really good for and the things that they're not so good for. So since most people haven't seen this potential outcome notation, let me introduce this notation, and then we can talk about randomized controlled trials in the context of this notation. Okay. So this is notation that follows Jerzy Neyman. Donald Rubin, who's a statistician, kind of also developed this notation in the mid-70s, and there was a big fight between, whether we should call it Neyman notation or Rubin notation. Since I'm from Berkeley and Neyman was a Berkeley statistician, I refer to it as Neyman notation, but some people call it Rubin notation, so I compromise and call it Neyman-Rubin notation. So this is a notation in which you basically think about each person. Let's index each person, say in this room by I, and let's think about a particular treatment. Let's say it's a pill that's designed to improve, when you have a headache, you take the pill. And for each person, there are two outcomes. So the outcome if they take the pill, let's call that YI1, and the outcome if they don't take the pill, which is YI0, right? So let's say this is the world we're in. Each person has two outcomes. Okay? So this is kind of the key insight for Neyman notation, which is that for each unit in the population, that unit is characterized by two random variables, their outcome when they receive the treatment and their outcome when they don't receive the treatment. So that's YI1 and YI0. Okay? So these are importantly latent outcomes. Okay? These are outcomes that are inherent to each individual, but not for any given individual, only one of those two is going to be observed. Right? So for any given individual, either they receive the treatment, in which case you observe Y1, or that individual does not receive the treatment, in which case you observe Y0. Okay? So when you think about causality in this way, one of the things that jumps out at you is that essentially trying to infer causality is basically a missing data problem. Right? If I could observe Y1 and Y0 for each individual, then the effect of the treatment is, whatever I wanted to learn is entirely embedded in Y1 and Y0, right? So if for everyone in this room, I observe both their Y1 and Y0, I could look at whatever I wanted to for that joint distribution of Y1 and Y0, right? I could look at the correlation between Y1 and Y0. I could look at the median of, say, the difference between Y1 and Y0, or any other quantile of the joint distribution, or any aspect of the marginal distribution, right? So think about if I could observe Y1 and Y0, basically I could observe, that's equivalent to observing this joint distribution of Y1 and Y0. And once I know this joint distribution, I can compute any functional of this joint distribution, right? Whether it's a mean, whether it's a median, whether it's a correlation, or what have you, right? So the key is this joint distribution between Y1 and Y0. The problem is that I can typically never observe this joint distribution. Okay? And the reason is because for any given individual, I can only observe their outcome if they receive a treatment. So if everyone in this room received the treatment, I would only observe Y1 for everyone. If everyone in this room didn't receive the treatment, I would only observe Y0 for them, right? And so then I would only observe the distribution of Y0. And for any given individual, I would never observe Y1 and Y0 together. Okay? So that's kind of the fundamental problem of causal inference, or one way to view the fundamental problem of causal inference is that you can never observe both outcomes for the same individual, which is sort of what you need if you really want to talk about causality, right? I really want to answer the question, if I take the pill, will that remove my headache, right? So that's really sort of saying, for me, what is the difference between Y1 and Y0? What's the comparison between Y1 and Y0, right? So that's this fundamental insight behind Neyman notation, behind Neyman-Rubin notation for counterfactual outcomes. Now, one way to view this, one way to think about randomized experiments is to think about randomized experiments as being a way in which you can learn about some aspects of this joint distribution of y1 and y0. Okay? And so how do we introduce randomized experiments in this notation? We introduce this new variable called ti, which is an indicator for treatment, which is equal to 1 if person I receives the treatment, is equal to 0 if person I doesn't receive the treatment. And let's say we're in a world in which ti is completely randomly assigned, so have complete control over whether a person receives a treatment or not. Okay? And so in that case, if ti is randomly assigned to each individual, so within each individual in this classroom, I toss a coin, and if it comes up heads, I assign them to treatment, and if it comes up tails, I assign you to control, then I should have independence between ti and anything else about you as a person, right? So in particular, I should also have independence between you, between your y1 and y0 and your treatment assignment, right? Because the reason I'm assigning you treatment has nothing to do with your characteristics, right? Has nothing to do with your y1 and y0. It's just a coin toss, which is independent of everything else. Yes?
So you are defining yi as outcome, so wouldn't it depend on the treatment? Like if I'm getting a treatment, say I am getting vaccination,
Yeah.
so wouldn't that affect my health outcome? So why would it be perpendicular to yi1?
So yi1 and yi0 is basically saying that you have a particular response to treatment regardless of whether you receive the treatment or not, right? So me as a person, either I respond well to the pill or I don't, right? Now, how I respond is of course going to depend on when I take the, what you observe about me is going to depend on whether I take the pill or not. So my observed outcome is going to depend on the treatment assignment. And so that actually is going to be shown right here, because I'm going to draw a distinction between yi1, yi0, and the outcome I actually observe, which is yi. Give me 2 lines and I'll get to your answer. Okay? So this is randomization. Okay? So the other key part of the Neyman-Rubin notation is what's called the stable unit treatment value assumption, which is to say that my assignment to treatment doesn't affect your outcomes. Okay? So which is to say that, look, there's n people in this room. It could be the case that my response is a function of everyone else's treatment status in this room. Okay? So in principle, what I've called yi1 could really be, in principle, I could really think of this as being a function of the treatment status of all the n people in this room. Okay? Now, of course, for the particular example I've given you, this is not realistic. Whether my headache improves or not shouldn't depend on whether everyone else in the classroom gets a pill or not. But of course, like the example you gave, which is a vaccination example, this would clearly be relevant, right? So if 49 people in this room are vaccinated against polio, then the 50th person, presumably their outcome, or polio maybe is not the great example, but think of any kind of contagious disease, right? There's herd immunity. If conventionally the idea is if 90% of the population or 95% of the population is vaccinated, then even if a small fraction are not vaccinated, it doesn't matter, right? So that's a world in which giving treatment to other people actually affects my outcome, right? And so this is something that traditionally is ruled out in the Neyman notation, because it says, look, the only thing that matters is your own treatment status. Okay? So what is this YITI? So this YITI is actually the object that you were referring to. This is the actual observed outcome. It's a function of the treatment that you actually receive, right? So YITI, okay, this is the actual observed outcome I see for every person, okay? So it's yi of ti, and what is yi of ti? Yi of ti is just defined as yi1 times ti plus yi0 times 1 minus ti. Okay, and ti is a binary variable, so ti is either 1 or 0. So this is really just simple algebra for basically pointing out that if treatment is equal to 1, then I observe yi1, right? So if you observe the treatment, I observe your y1. And if I don't observe, and if you are assigned to control, in other words, your ti is equal to 0, then I observe your outcome in the absence of the treatment. So that should answer your question, right? So for my observed outcome is yi, and the observed outcome depends on whether or not I get the treatment. If I get the treatment, I observe the outcome when I've taken the pill, right? If I don't get the treatment, then I just observe the outcome when I don't take the pill. Yeah.
I'm quite still caught
Okay.
in
Okay.
Yeah, like because maybe I'm not. So
Okay, so but these are two different, you can think of this as two different concepts. So right now, so randomization is going, so this object that I've written here is totally independent of whether I randomize TI or not. Okay, so the randomization, in fact, if I were to rewrite these slides, I would probably introduce randomization in this bullet point here. So everything I've written here, so if you just ignore this randomization point, everything I've written here doesn't have to do with randomization. Does that make sense? Okay. So then you want to go back to that question, or? I mean, I guess the other way to think about it is, let's see. So I guess so we can think of an economic example, right? So let's say that we're trying to look at the impact of remedial education class on test scores, okay? And so TI is equal to 1 if I take the class, and TI is equal to 0 if I don't take the class, okay? And let's say Y is some test that I'll take 1 month, after the class, ends, and that's the score on that test. What this way of thinking about the world says that for me as a person, or for you, you have two outcomes already. One outcome is what would be your test score in the exam if you took the class, and one is what would be the outcome if you didn't take the class. Okay, so that's Y1 and Y0. Okay, so let's say for you, the outcome if you took the class is 100, and the outcome if you don't take the class is 50. Okay, now the issue is that for you, I'm only going to observe what happens if you either take the class, in which case I'll observe 100, or if you don't take the class, in which case I observe 50. Right? I'm never going to observe for you both 100 and 50. Right? I'm just going to observe one of those. Whereas when I'm trying to understand the effect of the class is kind of the difference between these two, right? The effect of the class is for you, right? And the same holds for everyone in this classroom, right? So let's say for me, if I take the class, my score is 80, and if I don't take the class, let's say my score is 0, right? So for me, the class has a huge treatment effect, right? For you, the treatment effect is much smaller. But the fundamental problem is, let's say I take the class, so I get an 80, and you don't take the class, and so your observed score is a 50. Right? So then we're left with kind of a data set where some people have taken the class, some people haven't taken the class, and then we ask, what can we learn about the effect of the class from that data? And in fact, that's where the randomization comes in. If we randomize, then we can at least learn something about this joint distribution. Okay? So how much of this is still confusing? How much of this is okay? Yeah.
So we define yi1 as yi when conditional on ti is equal to 1.
No, yi1 is not conditional on ti is equal to 1. So these are not conditional statements, right? So this is define yi of ti as yi1 times ti and yi0 times 1 minus ti. Okay, so this new variable yi, okay, is equal to this object here. So if I try to condition yi on ti is equal to 1, right, that's going to be the expectation of yi1 conditional on ti is equal to 1. Okay, does that make sense? So yi is equal to yi1 times t plus yi0 times 1 minus ti. Right, and so this is actually maybe a good way to introduce it. So you're asking about these objects. You're asking the expectation of yi given ti is equal to 1 and the expectation of yi given ti is equal to 0. Okay, so can everyone see this at the back? Yeah. So the question was, how do we relate, say, expectation of yi given ti is equal to 1 or the expectation of yi when ti is equal to 0 to these objects here? Okay. So just by looking at the definition of yi, we know that this expectation is going to be the expectation of yi1, right, conditional on ti being equal to 1, right? And we know that this object here is going to be the expectation of yi0 conditional on ti equal to 0, right? So how do we interpret this? This is the average outcome amongst all of those people who take the treatment and the average outcome amongst all of those people who don't take the treatment. Okay? So this is really when randomization comes in, because randomization basically says if I have randomized ti, right, this ti should be independent of y1 and the ti should also be independent of y0. So in fact, if you have randomization, right, then this should just be equal to the expectation of y1. This should just be equal to the expectation of y0, right? So this is really where randomization comes in. It allows me to go from here to here, right? Because Ti is orthogonal to y1 and y0, the conditional expectation is just going to be equal to the unconditional expectation, right? And so here, as I say, what happens then is that if you look at the difference in, say, means between the treatment and the control group in a randomization in an RCT, then what you get is this object here. And this object here has a nice interpretation. It is the average difference between y1 and y0, right? So this is the average treatment effect, right? So what an RCT does is it doesn't give you the difference between y1 and y0 for everyone in this room, but it gives you the average difference between y1 and y0 for everyone in this room, right? So it recovers what's called the average treatment effect, right? And that's basically kind of the power of an RCT. It allows you to recover an estimate of the average treatment effect, okay? So does this make sense now? Yeah? Okay. So this is really kind of fundamental to thinking about randomized controlled trials, and really what's the power of a randomized controlled trial? Like, why are people spending millions of dollars just to go from here to here in this equation, right? What allows you to kind of remove this conditioning?
So one clarification, like this,
Yeah.
if this condition does not hold, it means there is selection bias.
Yes, right. So, or essentially, if this condition does not hold, it means that the treatment assignment is correlated with y1 and y0. That's another way to call it, another way to term that is selection bias, right? So one way to say that is like, you know, in the context of in the context of observational data and say the remedial education class, let's say that only the kids who would really benefit from the class take the class, let's say, okay, if you don't have a randomized control trial. Then there would be correlation between T and y1, right? And the fundamental problem behind a lot of correlational work in economics and in other fields is that usually in a model, in a world where people are choosing TI, where people are choosing the treatment, they're typically choosing it as a function of y1 and y0. Because while I, as the econometrician, don't observe y1 and y0 for each person, it's reasonable to assume that the person themselves may have some idea of their y1 and y0. Right? If a person is deciding to spend a lot of money to take a class, presumably they're only going to take the class if they think they're going to benefit from it, right? If I think I'm not going to benefit from the class, then I'm not going to take the class, right? And so if you're just looking at observational data, then that kind of thinking is going to generate a correlation between whether or not you take the class and your potential outcomes under that class, right? So that's kind of the fundamental problem. Now, of course, even in randomized controlled trials, there may often be problems like this, and we can talk about some of those later on. But the kind of the best case scenario is one where basically, you know, you're assigned to treatment, you take the treatment, and the treatment is completely orthogonal to y1 and y0. Okay. In randomized controlled trials, we'll talk about some of the other problems, but one of them is like just because you assign someone to treatment doesn't mean they have to take the treatment, right? So that's one problem. All of the theory you really need to understand randomized controlled trials and kind of the power for where the power of a randomized controlled trial comes from. It allows you to remove this conditioning, right? Okay. Now, so let's talk about what are some of the problems with randomized controlled trials. So presumably the first set, you know, you've seen some version of randomized controlled trials in all of the 3 lectures before. This maybe just puts a little bit of notation on that description. This I'm not sure if you've seen before, so let's spend a little bit of time on this. So this is kind of what are the possible critiques of randomized controlled trials. Okay, so one way to think about it is just to go back to this idea that, look, each person has a y1 and y0. Everyone in this room has a y1 and y0. If I knew what their y1 and y0 was for each of you, really what I would know is this joint distribution of y1 and y0. And that's really the object of interest for me as an econometrician. I really care about f of y1, f of the joint distribution of y1 and y0. And why is that? And that's because I might be interested in many different functions of this joint distribution, right? So for example, I might be interested in the median treatment effect, right? Instead of looking at the, instead of thinking about this object, which is the average treatment effect, I could really be interested in the median of the treatment effect, okay? So I want to compute y1 minus y0 and take the median of that object, right? So say If I knew y1 minus y0, I would compute y1 minus y0 for everyone in this classroom, and I take the median value of that, right? So that would be the median treatment effect, okay? So the problem is that the median treatment effect is not the difference in the medians between the treatment and the control groups, okay? So what this is kind of the simplest example that shows you that a randomized control trial doesn't often give you everything that you are interested in. It gives you the average treatment effect. Okay, just comparing the mean in the treatment group to the mean in the control group will give you the average treatment effect. Okay, but comparing the median in the treatment group to the median in the control group doesn't give you the median treatment effect without further assumptions, right? And the whole power behind a randomized control trial is that it tries to minimize assumptions, right? Once you spend these millions of dollars in going from here to here, then basically tells you that I can compute the average treatment effect without making a ton of assumptions on how people behave or other things, right? Here's a simple example where you're just interested in something that, typically there's no reason to be interested in the mean more than the median, say, right? There's no theoretical reason necessarily that one is more interesting than the other. But if you're really interested in the median, then just doing a randomized control trial will not give you the median treatment effect without further assumptions, okay? So randomized control trials are great for computing average treatment effects, but they're not going to give you a median treatment effect without further assumptions. So that's one problem with randomized control trials. They kind of only give you one aspect of this joint distribution, right? If you think about why that is, one intuition you can get is that the expectation operator is linear, so the expectation of y1 minus y0 is in fact equal to the expectation of y1 minus the expectation of y0, and because that's the case, then you can compute each of these separately by looking at the treatment and the control means, and you can compute this. But the median treatment effect, but the median of y1 minus y0, which from your intro econometrics courses, you should know that the median of the difference between the two medians is not the median of the differences, right? And because of this, you can't just look at the median of the treatment group and the median of the control group and compare the two. Okay, so this tells us that randomized control trials are good for some things, but not for others. In addition, there's a whole bunch of other problems with the sample that you choose for a randomized control trial, which could affect the results from the randomized control trial, right? So selection bias, someone already raised. So this is the problem that just because I assign you to treatment doesn't mean you actually take the treatment, right? So just because I assign you to attend the remedial class doesn't mean you'll actually attend the class, right? That's selection bias. Attrition is a version of selection bias too. That's just, I start attending the class, but 2 weeks into the class, I drop out from the class, and that is not random. Maybe I drop out because I'm not learning anything in the class, or I drop out because I've learned everything I need to learn. And so that, again, is going to break this independence assumption, right? Non-compliance sort of combines both of these, but in general, you give me a pill, there's no reason I may not take the pill, right? So that's a version of attrition. So that's kind of problems that have to do with the implementation of the trial and the running of the trial. Then there's kind of more conceptual issues with thinking about randomized control. Yeah?
So I also had in part that in the progress method, but in case they're interested in that,
Yeah.
you say that such assumptions.
Yeah.
What would that be?
So those are typically what I call kind of rank monotonicity assumptions. So the idea is that you place an assumption on the distribution of y1 and y0 and sort of say under the treatment, a given quantile of y1 is only going to move in one direction. So like you're not going to, so it's something, so it's effectively essentially saying that if you're in the median under t is equal to 1, then, and if you move up, let's say under y1 relative to y0, then that's going to be true for all quantiles. So they're typically known as rank monotonicity conditions. Now, of course, those can be reasonable. You might ask, like, look, if a remedial class helps the worst student in a classroom, it's not going to have a negative effect on, say, the second worst student or the third worst student. So in that context, it's reasonable, and then you can estimate it by looking at the difference of the medians. But the point here is to say that you need to make that assumption, and in order to make that assumption, you need to know something about the intervention. Whereas the average treatment effect, you don't need to make any of those assumptions. So the other problem with the randomized control trial is really kind of conceptual, which is to think about what is our object of interest, right? So one object of interest, it could be just, I want to learn about whether this particular remedial class works, and the randomized control trial might give me an answer for that. But in general, as an economist, often as a policymaker, you might be interested in learning about what happens in a remedial class that kind of looks similar to the class that's in the experiment, but is slightly different. Let's say I have better trained teachers or worse teachers, or I have a different sample of students that are different from the ones that are in the randomized control trial, right? So I run my randomized control trial on one set of schools, but I'm interested in learning about what the effect would be if I run it, but if the program I want to run is actually in a different set of schools, right? So if I run my randomized control trial on a set of private schools, but I really want to implement my policy on a set of government schools, right? You might think that I might learn nothing from the randomized control trial because private schools are just so different from government schools that anything you learn from a private school may be not useful in a government school context. Right, so how do we really use RCTs to learn about unimplemented intervention, to learn about kind of different policies is a broader way of thinking about this. So that's one issue with randomized controlled trials, right? You have to make additional assumptions to think about this, right? And similarly to think about the quantile treatment effect. Another problem is deviations from this stable unit treatment value assumption, which is this assumption that my outcome is only affected by my treatment and not everyone else's treatment. We talked about vaccination as being a simple example where that's violated, but in economics, in your first year micro, you spent kind of a whole probably couple of months talking about a very specific economic concept which suggests that this would be violated, right? Which are general equilibrium effects or externalities, or the idea that essentially what goes on in an economy, general equilibrium effects, and those might mean that my outcome is affected by everyone else's treatment status, right? So you might think, so there are simple ways to think. There are simple examples that you can use to remind yourself of the importance of this. So think about an RCT of a job training program, right? You run a job training program, you randomize some people into receiving job training and some people into not receiving job training, and you follow these people 3 months after the program ended, and you see, oh look, there's this 10% effect on employment rates for people who've taken the job training program. Now that makes sense if the overall labor market, if the fraction of people who are getting the job training program is a small fraction of the overall labor market. But what if you offer the job training program to 100% of everyone in the labor force, right? Then the general equilibrium effects might be very different, right? Because now everyone is trained. So for a particular employer, just because you have training doesn't mean you are attractive anymore because everyone they know is trained, right? So it could be that in GE, the effect of that labor training program is zero, because it doesn't distinguish between participants anymore. But in a partial equilibrium setting where you're only running an RCT on a small set of people, you might think this effect actually is significant, right? And so this is actually a pretty important problem with thinking about RCTs and how to thinking about scaling up RCTs, right? In particular, you run RCTs on kind of small areas, and you want to ultimately perhaps use it to inform policy, but typically policy is typically thinking about scaling up these programs. And so when you scale up program, you have to worry about these general equilibrium effects, okay? Then there's kind of a narrower concern, which I call Hawthorne effects or John Henry effects, which is just like being in an experiment is going to affect your behavior, right? Just the fact that you're in an experiment is going to affect how you behave, right? And this is particularly relevant for economic experiments where effort is kind of a key variable. If you take a pill or not, then as long as you take the pill, presumably it doesn't matter. Like you can't exert less or more effort. Your body's just going to respond to the pill. But if you take how hard you study in a remedial class, how hard you work in a job training program, all of these things require effort levels, and maybe if you're in an experiment, it's going to affect how hard you're going to work. Okay, and so these names come from kind of a original set of what are called time motion studies that were carried out in the 1920s by Frederick Taylor, who's kind of this big management guru, who did all of these very kind of ran these experiments in a factory in Massachusetts, I think. And he tried to see what happened to workers when you kept the lights on low, you kept the lights on high, and he found that in fact didn't matter. You kept the lights on low, the workers responded in one way, you kept the lights high, the workers responded in the same way. And the traditional explanation is that the workers knew they were part of an experiment, and they knew there were all these people watching them. So it kind of didn't matter what the experimenter did, they just knew there were these guys watching them on the shop floor, and so they just performed better. Right? So that's just the idea that being in an experiment is going to affect your behavior, and that's very relevant for economics because typically the kind of experiments we study, behavior is kind of a key component, and we still have a pretty poor understanding of how people's behavior varies within an experiment. So this is sort of a general, so more generally you can think about external validity, which is what I've been talking about, sort of these Hawthorne effects or the G effects. They all can be encompassed within this notion of external validity concerns. How externally valid is an RCT? So everything I've talked about here is really internal validity, which is to say that within the context of the sample that you have, if you run an RCT, you get an internally valid estimate of the average treatment effect. So for the sample you're studying, in the context you're studying it, you're kind of doing a good job. But how you can take that elsewhere is the idea of external validity. And for an RCT, that typically is a concern. And the last thing I'll point out that some of these things are not specific to randomized experiments. They are true even if you have observational data. Typically in observational data, we have methods that try to deal with these issues, right? So if you have GE effect, you try and write down a model of the labor market that tries to sort of explicitly model how the GE effects take place and take that to your data. You try to explicitly model selection bias or attrition in a way that allows you to get around this, right? So some of these concerns are not valid to randomized experiments, and the ways of dealing with this do exist in economics for at least some of these questions, right? Okay. Yes? Question? Can you control for these effects? Sort of depends a little bit on how you mean by control for. So one way people control for it is to change the object of interest, right? So what I mean by that is in a gold standard RCT, you assume 100% of people who you assign to treatment take the treatment, 100% of people you assign to control don't take the treatment, and then you compute the average treatment effect, right? But let's say you're in a world in which there's imperfect compliance. Let's say I assign 50% of people to a remedial education class. I assign, of the treatment group, only 50% of people actually take the remedial class. And in the control group, 50% of people actually end up taking the remedial class. So that's a world in which you have treatment non-compliance. Okay? So the way people deal, so there's two typical ways in which people deal with this. One is to redefine the object of interest. So now the object of interest is not, you redefine it to say, look, my object of interest is not the effect of taking the class, but the effect of being assigned to take the class. Okay, so it's not just semantics, it's actually a pretty big conceptual difference. Then you can still compute this comparison. You look at your treatment group and you compute the average test scores for everyone in the treatment group, regardless of whether they took the class or not. Similarly, you look at your control group and you compute the average test scores for everyone in the control group, regardless of whether they took the remedial class or not. And then you compare this difference. But now this is what's called the intent to treat effect. Right? Instead of the average treatment effect, it's the intent to treat effect, because what it's capturing is the intent to treat, or the effect of being assigned to treatment, rather than the effect of being in treatment. And some people think that's a reasonable parameter to be interested in, because look, in any given policy that you're thinking of implementing, some people are just not going to do the policy that you ask them to do, and we should not, we should incorporate that into our analysis. So that's one way to, quote unquote, control for non-compliance. The other way to control for it is to use instrumental variables, right? So in that particular, so you've all seen instrument IV before, two-stage least squares, just show of hands. Okay, so you've all seen two-stage least squares, right? So here what you would do is you would run a regression of the outcome on whether or not you attended a remedial classroom, a remedial class, and you would instrument the remedial class variable with treatment assignment. Okay, so now that's a different parameter of interest. That's typically what's called the local average treatment effect, and that is typically not equal to the average treatment effect, right? So basically the ways to deal with non-compliance are typically end up being ones where you kind of change the object you're interested in, right? Okay. Yeah.
So basically the randomization, theoretically speaking, looks straightforward. But in the field,
Yeah.
practically, how easy it is to ensure 100% randomization?
It's a good question. The question is, how easy is it to ensure randomization in the field? And I think the answer is difficult. So I think especially it depends on how much control the experimenter has over the program. So if you are working with an NGO, you have a good working relationship with the NGO, and you're running an RCT in that kind of context, you may have some more control over how much, whether someone who's assigned to treatment gets the treatment or not. But if you're trying to run an RCT with the government, say, right, then typically it may be much harder to ensure compliance, because maybe there's political concerns, or maybe there are other government, even ethical reasons why the government feels that, we can't hold out treatment to a certain group of people, even though theoretically you might like them to. So in practice, I think this, even though in theory we say Ti is orthogonal to this y1 and y0, in practice you kind of, in most papers in development, typically you'll have a section in a paper that will talk about, how much deviation was there from the experimental protocol. So same answer that I gave earlier, which is one way is you just redefine your object of interest to say I'm just looking at intent to treat. And indeed, in most development papers, typically the parameter that they'll present to you is going to be the intent to treat effect. They'll look at the difference between treatment and control for whatever outcome, but the interpretation will be this is an intent to treat effect, which is just saying that, look, I know that not everyone in treatment took treatment, not everyone in control remained in control, and so as a result, I'm going to interpret this treatment control comparison as an intent to treat effect. So it's the effect of being assigned to treatment.
One more question.
Sure.
May sound silly. So basically, if I'm a researcher and I'm going to a village,
Yeah.
which household and which lane to pick first? How do I decide? Because theoretically, you toss a coin and decide, but practically.
So you mean how you actually implement the randomization? So that depends a lot on what kind of resources you have. So I have done studies where we have carried out a household listing for each village, which is very expensive because you basically have to do a household census. And once you have a household census, you can just randomly choose households. Other studies have carried out protocols where you basically institute a protocol where you tell the surveyor to go stand at a particular point in the village and then choose a particular lane, go to like the fourth house in the lane, etc. But the idea is you take all of the subjective choice out of the surveyor's hands, right? You kind of try to write down a protocol where the surveyor has no choice in which household to pick. He kind of is following a rule that you have set out for them, right? And so that's, I think, kind of at least administratively, the way to write down the protocol. Now, whether the protocol is followed in practice is another problem, right? So then you need to make sure you have a research team with at least, 2 or 3 people. Usually one of them is someone you can, trust.
What would you suggest to a student, PhD student who has limited resources and a limited team? So how to ensure like the best kind of randomization?
First, I think for grad students to run experiments is very ambitious, right? Because you can spend 2 years designing experiment, raising money from it, and then experiment could fail for many reasons. The treatment protocol is not followed, or the treatment effect is 0. But I think there's just a lot of presence in the field is what I would say. Like, I think the big advantage that graduate students have over faculty is that they can afford to spend a lot more time in the field, right? For faculty, you have to teach, you have to advise, so you kind of need to be, at your university. But for grad students, you can spend like 6 months in the field, if you can. And I think if you have a limited budget, kind of replacing money with time is, for grad students, I think maybe one option. Yeah.
So, like you just mentioned a lot of development on this paper to, kind of like show us the intent to treat results.
Yeah.
But then, what is the threshold till which you can see that these results are valid, and even in this context it can be applied? So I'm trying to understand what standard deviation is it acceptable instead of,
You mean how much non-compliance is acceptable?
Yeah.
It's a good question. I think that's subjective. I don't think there's any kind of agreement on that. But usually most papers will tell you how much attrition, how much compliance there was, so you can kind of make up your own mind on, what you think that is. So one thing you can do is, if they show you the intent to treat effect, and if they also show you here is what the compliance rate is in the treatment group, here is what the compliance rate is in the control group, you can compute an IV also directly. Right, so then you can kind of look at the IV and see whether you believe whether you think the IV is a more reasonable parameter for you to be interested in. But IV again requires more assumptions than an average treatment effect, and so maybe you find that less convincing. So usually I think what I see in most papers is they give you the compliance rates for treatment and control, and they give you the ITT. So then it's kind of, but they may not always compute the IV for you. But you can always just, once you have those 4 numbers, you can compute the IV yourself, right? So do you people know like how to compute the IV for, if basically you have a randomized experiment with imperfect compliance, right? Then as long as you have 4 numbers, you can kind of compute the IV. And so what are the 4 numbers you need? You need the average outcome in the treatment group and the average outcome in the control group. Okay, so this is the ITT, right? The difference between these two is the ITT, and you just divide this by the average. So now let's let D be your actual, whether you take the treatment or not. And T is the treatment assignment variable, which is the same T as here. So you have the average compliance rate in the treatment group, and then you have the average compliance rate, or the average rate of people taking the treatment in the control group. And so if you look at this ratio, that gives you the IV. This is sometimes called the walled IV. And so most development papers will give you all 4 of these numbers. So you can compute that as another way to figure out, what you think the effect of the treatment is. Okay, other questions? Yeah. Well, how to interpret this? Yeah, so this is, you were assigned to take the treatment, so you were assigned to take the pill, you were assigned to not be in the remedial classroom, but you ended up taking the class anyway, right? Because the experimenter couldn't stop you. Yeah. Okay, so this is so far kind of an introduction to randomized control trials, and now I realize I'm running very short of time. Let's talk a little bit about structural models. So this, I think, is something you should be more familiar with given your coursework, and this is just this idea that your starting point here is from the economics of the problem. You start off with a well-defined economic model, right? So you write down person's utility function, you write down their endowments, you write down the technology, you write down whatever constraints they're facing, and you write down some rule for behavior, which is typically some kind of optimization. People are maximizing utility subject to a budget constraint, right? That's kind of the starting point. And then all of the parameters in this model have an economic interpretation because you've written down the model, right? So every single parameter is either something that parameterizes, say, the utility function, right? It's the degree of risk aversion, or it's the time preference parameter. So everything here, all the parameters have a distinct economic interpretation, which is not necessarily true in a randomized controlled trial. What you're primarily interested in is an average treatment effect, which may or may not have an economic interpretation. Right? Here, your starting point is that all of the parameters have some kind of economic interpretation. Of course, there are problems with structural models. Right? The first thing is, who tells you that your particular model that you've written down is actually the right model, right? You are thinking in your head that here's the way the world works, but how do you know that's the way the world works? The world could work in some totally different way, and so we call that model specification problems or misspecification, right? And it's reasonable to assume that in econ, most models are misspecified in some way, right? The world is not really full of people maximizing utility, right? They might be doing lots of other things, and so your model is at best only kind of some imperfect approximation to that kind of world. The other is, in some sense, this notion of external validity, which is like you write down, say, a structural model for estimating, time preference parameters amongst health workers in Pakistan, which is kind of the project I'm going to talk about. How do these parameters, you've estimated some time preference parameters for this population of health workers. Is that going to be true for non-health workers in Pakistan? Is that going to be true for the population of Pakistan in general, right? You have, to what extent are these time preference parameters going to change if there's another change in the economic environment? This is a version of what in macro is called the Lucas critique. The idea that the parameters that you estimate are kind of a function of the particular economic environment you're in, and how do you know that those parameters are not going to change if the economic environment changes, right? And so the fundamental answer in some ways that you don't really know, right? But it's something that you always have to kind of worry about, right? Now, given kind of but let's say we've addressed these issues and you have a particular specified model, then the question is you have this model that you've written in your head or written on a piece of paper, and then you have observed data, right? You go off and observe some data, you collect a data set, or you use the NSS or the NFHS. And the question is, how can you map the model in your head to the distribution of the data that you observe, right? And this is the problem of identification in economics, right? So how do you take the model that you observe to the data that you collect, right? And the idea is, essentially being able to show that there's kind of a one-to-one mapping between the two, that, from the data you can identify one particular model, right? And so if you go back to this Coles Foundation stuff that I talked about in the beginning, this identification problem was central to simultaneous equation models, right? So I don't know if it's still taught, but when I took econometrics many years ago, right, we spent a big section talking about identification in simultaneous equation models. That was basically saying, you've written down this set of models in your head, you have some data, can I uniquely identify the parameters of this model given the data that I've observed? And so this identification becomes very critical to structural modeling in a way that you kind of don't see in a randomized control trial, because in a randomized control trial, you sort of set up the randomized control trial so that this particular parameter is cleanly identified, right? So that's the whole point of a randomized control trial, to allow you to cleanly identify the average treatment effect or the ITT. Whereas in a structural model, your parameters are, you know, a risk aversion parameter or a time preference parameter. How do you know those are identified, right? So that becomes a very central problem in structural models. Okay, so why should we use structural models, right? So structural models, in some sense, you can think of as being the complement of randomized control trials. They often allow us to do things that randomized control trials do not allow us to do, at the expense of making other assumptions, of course, right? So for example, you can understand, you know, since you can actually estimate these, since all of the parameters that you estimate have an economic interpretation, right, you can then try to understand the economics behind behavior, right? So this is like saying you can understand the underlying motives for people's behavior, right? Sometimes you can also test for some assumptions. So you know, there are papers that test for, you know, for example, profit maximization, right? So it turns out you can test for certain assumptions that you've used to build your model. So trying to uncover, let's say, the economic primitives of your particular context. The other use of structural models is to do extrapolation, right? So you want to study the effect of a particular policy in this environment that has not been implemented, right? You want to say, okay, I go out and collect, you know, I'm going to talk about a cash transfer program. You know, there's a cash transfer program that was implemented. The cash transfer program handed out, let's say, 500 rupees a month to households. What will happen if instead I handed out 5,000 rupees or, you know, 200 rupees, right? To answer those, so randomized control trial is typically not going to answer those questions, because a randomized control trial can maybe tell you very clearly what's the average treatment effect of handing out, say, the particular amount of money you do hand out in the trial. Let's say you hand out 500 rupees in the trial, you can look at the ITT for handing out 500 rupees, right? But if you want to ask what happens if I were to hand out 5,000 rupees, you need some kind of model for how the world works, right? And that's what a structural model should give you. And a value of structural model is in the jargon you call it counterfactual policy analysis. So trying to look at what happens when you implement counterfactual policies. Okay. And then finally, you can use the model parameters just to do welfare analysis. So if I implement this policy, what's the welfare impact going to be on households? So you can see kind of structural models kind of are much more closely tied into the kind of work you did in your first year, right? You did micro and macro. You wrote down all these kinds of models in micro and macro for optimizing agents. Structural models are trying to take those kind of models that you wrote down to the data. Okay, so that's kind of the value of structural models. They're more closely tied into the kind of work that you've done, coursework that you've done as an economist. Now, of course, they've had a whole set of concerns. So, you know, you can think of this whole movement in the early 1990s towards doing natural experiments as basically being a move away from structural modeling. So if you were to be doing your PhD in the late 70s or the mid 80s and you wanted to do applied econometric work, you would typically be writing down some kind of structural economic model and estimating it. Now, it turns out that there were lots of problems with these models, and this whole turn towards doing randomized experiments and natural experiments, you know, one view is that it just came from kind of a pessimism about the ability of these structural models to really tell us something about the world. And of course, there's huge arguments on all of these issues. But what are some of the criticisms people had in that period? So one is kind of, you know, you write down a structural model in I/O or in labor, it'll take you, you know, even in this day and age with all the computing resources we have, it'll take you 6 months to estimate this model, you know, get your standard errors right. But who's to tell you that this model is the right model, right? I mean, you don't really have a way to tell, is this the right model? What happens if the assumptions that underlying the model are wrong? And that's one reason why people, you know, structural models are always sort of problematic. You don't necessarily have a strong reason to think about why this particular model is right. So that's one problem. The other problem is that there's actually a big jump between the theoretical model you write down and the actual model you estimate, right? Because maybe you write down, you take your first year PhD micro course, you write down some utility function, you want to maximize it, and you want to take it to the data. But in that moving from the model to the data, you make a ton of assumptions that have nothing to do with theory, right? You say, oh, I'm going to assume that my errors are normally distributed, or my errors have a logit distribution. I'm going to assume that my utility function is CRRA or is something else. Nothing tells you that the world actually works that way. You only make those assumptions because it makes your estimation easier, right? Because you don't know how to do estimation if the errors have just some unknown form, right? So the problem there is that when you actually estimate the model and you test the model, you're testing jointly both the economic model And all of these auxiliary assumptions that you've made that kind of aren't really that relevant for your model, they just aren't that relevant for the theory, they're just there because they make the model easy to estimate. And so you're doing a joint test of both of these assumptions. And so if you reject, some particular, if you reject a model, say, you don't know, are you rejecting it because the economics is wrong, or are you rejecting it because the errors are just not normal and you assume they were normal, right? So that's one problem with structural models. Something else that's very common in structural models is you spend 6 months estimating a structural model, and then you go in and say, oh, I'm going to just change the utility specification a little bit. I'm going to change, and then you find that your results completely change. Right? So this is this non-robustness for structural models, and this is very common. If you've ever estimated structural models, you see that often there's a lot of very big changes in the parameters you estimate for relatively small changes in the specification of your model. There's a question? No? Okay. And then finally, there is this idea that the model may not itself be identified, right? So it could be the case that two different parameter values may be consistent with the observed data, but these two different parameter values might have actually very different economic interpretations. Okay? So this is kind of going back to this identification problem, right? And so this is one reason, so this is one slide that sort of summarizes a lot of problems with structural models. And in some sense, you can think of the fact that people started looking for natural experiments and IV as basically people saying, look, these problems are just so big and so intractable that we're just not even going to estimate structural models anymore. We're just going to try and do randomized experiments, or we're going to try and do, look for natural experiments in the data. Now, of course, that's going to limit the kind of questions you can answer, because you can't then answer all of these kinds of questions that structural models were designed to answer. So that's kind of a brief introduction to RCTs and structural models. What I want to do now is just give you a particular structural model, just a very simple structural model, and then I'll talk about how we might think about estimating this model, and then I'm going to talk about how you might run a randomized experiment that is going to try and identify aspects of this model. So here, what the starting point is going to be for the rest of this lecture, that we really want to combine the two approaches. We would like to use randomized experiments, but we would like to use them to learn something about an economic model of the world that we already have. Okay, and so then how do we design an experiment to learn something about this model? Yeah.
So from an application point of view, how important is it to have a good identification strategy in structural modeling paper as opposed to just finding out the value?
So it's a good question. I think that nowadays the emphasis on having identification is pretty high, in the sense that most structural papers that you read now will typically have a pretty big section on why they think their model is identified. Now, not all of them will have a formal proof of identification. So if you go back to the Scholes Commission, identification requires a formal proof. You have to write down some kind of theorem that says my model is identified. There's a one-to-one mapping between the data and the model, or the inverse is one-to-one. Not all papers have that formal proof, but they will have some versions of that. So there's a recent paper by Isaiah Andrews and co-authors that kind of talks about how you can test to see where the identification in your structural model is coming from by running a series of kind of OLS regressions. All that to say that basically now, if you write a structural model and you estimate a structural model, you should have a section that talks about identification, which wasn't true like 20 years ago. 20 years ago you wrote a model and you kind of identify. You presented results without, you would talk about identification, but it wasn't 10 pages of your paper. It was maybe 2 pages. Other questions? Yeah. Oh, it's Andrews, Genskow, and Shapiro. And it's in the QJE. I don't know what year. I think the published version came out like maybe 2 or 3 years ago. Yeah. Yeah.
This one says that because considering the new policy environment, it may not work in the counterfactual scenario.
Right.
Doesn't that even hold for an RCT where
Absolutely.
you can't just-
Yeah, so in an RCT, we would call it external validity.
Right.
Yeah, absolutely.
In that case, if I had to compare the SM versus RCT,
Yeah,
both are not helping me kind of step anything into outside world
yeah.
beyond the context of this. So in that case, what is like the best
So yeah, so I think both of them have issues with this external validity. I would make the argument that for structural models, you can be very explicit in where you think the external validity doesn't hold. Like you could say, I have a structural model for lady health workers in Pakistan. I estimate this time preferences for them, and the reason I think this model will not apply to male health workers is because I think male health workers have very different time preferences than female health workers. Or the reason why I think it will apply is because I think they have the same time preferences. So in some sense, I feel with structural models, you can be very explicit about where the external validity fails or does not fail. But you could make similar. You could sort of say something similar about randomized experiments, because these are kind of loose arguments, right? You could say, oh, randomized experiment about small class size in Kenya is more relevant for India than for the US, but it's kind of a loose. It's not necessarily a formal argument. Okay, so this is an example for so the starting point here is I'm just going to write down a simple dynamic choice model, and I'm going to talk about what is the value we can add by trying to do some structural modeling and to use a randomized control trial. Okay, and the point I want to make is that we can actually answer some very we can try to answer some very basic fundamental questions that are still kind of open, and that's why this is kind of an exciting area to work in. And the reason I picked this example is because hopefully you should have seen some version of this kind of dynamic model in your first year courses. Okay, so hopefully it will also going to be relevant. It should also hopefully be kind of a refresher for your first year courses. So it's a very simple dynamic choice model. We only have a 3-period model, so period 0, period 1, and period 2. It's a single agent model. So again, this is a very simplified model. Agent's behavior doesn't depend on anyone else's behavior. It only depends on her own behavior. It's only going to take action in 3 periods. I'm going to assume away uncertainty. There's no uncertainty in this world, and the answer and the choice problem is, of course, very straightforward. I'm only going to choose in periods 1 and 2 the number of tasks I'm going to perform in period 1, the number of tasks I'm going to perform in period 2. Think of this as in period 1, I'm going to choose how many vaccinations to carry out. In period 2, I'm going to make the same choice. So basically, figure out how many vaccinations I'm going to carry out. And this is because the application I'm going to talk about is an application about health workers making choices about how many houses they're going to approach to carry out polio vaccinations in Pakistan. Okay, so I'm going to also make a whole bunch of assumptions that, again, are ad hoc in the sense that we don't know if these hold in practice, right? But they are what make the model tractable. They are what make the model easy to estimate. So the first thing is I'm going to assume that preferences are time separable. So in any given period, my utility in that period only comes from the actions I take in that period. So I rule out things like habit formation, that what I did last period affects my utility in this period, or like anticipation effects, right? All of those things are ruled out. So this is just to point out that even when you write down a simple structural model, you're actually making very strong assumptions about the way in which the world works. And so we shouldn't forget that. So here is what the utility function for my agent is going to look like in period t. Because of time separability, I can sum utility across the different periods from little t to capital T. So that's the time separability allows me to make the summation. In any given period S, my utility in period S is given by US evaluated at AS, which is the number of actions the agent takes in period S. And then I'm going to discount this utility back to period T using this gamma function. So this gamma ST is a discount factor. It says one utility or one util in period S is worth gamma ST utils in period T. Okay, so how do I discount back to period T my utility in period S? Okay, and so the reason I'm going to write it in this very general way is because I'm going to nest most of the models that you've seen in your first year depending on different specifications for this gamma function. Okay, and we're also going to test for which particular gamma function is actually we're going to test for different versions of the gamma function, right? So in some sense, this is kind of very fun. This is the discount factor. It's kind of a fundamental building block in all dynamic work, right? Whether you do macro, whether you do dynamic micro, the discount factor is kind of a key building block, right? How do you discount utility from period T, from period S back to period T, right? All models of dynamic choice have to take a stand on how this discounting takes place. Okay, and what we're going to do is try to ask what can we learn about this discounting. Okay, and so this utility here is the utility in period S from taking action A sub S, which is just the number of tasks I'm going to carry out in period S. I'm going to allow the utilities to change over time. So this utility is subscripted by an S. So utility in period 2 can be different be in utility in period 3. In future, we may also want it to depend on other observables. So when you actually estimate utility functions in practice, you might want to make this functions of other individual level observables that you see, say, education or something like that. Okay, but this hopefully is something that you have seen, except for this kind of at this point unnecessarily formal definition of the discount factor. This is something that you should have seen in kind of your first year courses. And then just to fix ideas, I'm just going to write down what this looks like in each of the different time periods. So at time period 0, what is my utility from taking action A0, A1, and A2? My utility is going to look something like this. This is my utility in the current period. This is gamma 0, 0, which is hopefully equal to 1, which is you don't discount utility in period 0 in any way. This is how do you discount utility in period 1 back to 0 by this gamma 0, 1 function. In period 2, you get utility U2. You discount it back to period 0 by using the discount rate gamma 2, 0. In utility 1, again, you discount utility in period 2 using the discount rate gamma 2, 1. This is how do you discount utility from period 2 back to period 1. And so one thing I want to point out is that there's sort of this distinction here, which is gamma 2, 0 and gamma 2, 1 need not be equal to each other. This is just saying how do you discount utility from gamma 2 back to period 0. How do you discount utility in gamma 2 back to period 1? And in fact, these two need not be the same either, right? This is saying how do you discount utility in period 1 back to period 0? And this is how you discount utility in period 2 back to period 1. So even though this is only a 1 period difference in utility, you could be in principle discounting them in different ways. Okay? So these are the 3 different utility functions, 3 different utilities evaluated at 3 different time periods. Okay? And the key object that we're going to use to study the nature of discounting is going to be this discount ratio. Okay? So what at t is equal to 0, I'm going to compare the ratio of the discount rate between period 1 and 0 and between period t and 0, right? So the numerator is just how do I discount period 1 utility back to period 0, and the denominator is how do I discount period t utility back to period 0, and I look at the ratio of these. Okay? And this ratio will be important later on. And then at t is equal to 1, this is exactly the same object. This is in period 1, how do I discount utility in period 1 back to period 1? So hopefully that should just be a 1, right? But I'm going to allow for generality and just call it gamma 1, 1. And the denominator is in period 1, how do I discount utility from period t back to period 1? Okay, that's the gamma t1 discount factor here. Okay, now supposing we want our agents to be time consistent. Okay, what does it mean for agents to be time consistent? Now in most of your first year, unless you've kind of done models of time inconsistency, you typically always assumed implicitly that your agents were time consistent. And what that means is that these ratios have to be the same. Okay, so essentially it's saying the rate at which you discount utility in periods, the relative rates at which you discount utility at period 0 is the same relative rate at which you discount utility in period 1. So this is time consistency. That makes this assumption. In addition, supposing we assume that this discount factor only depends on how far ahead you are discounting from. So in other words, if gamma s comma t is actually equal to gamma s minus t. In other words, utility that's in other words, when you're looking from, let's say, period 1 to period 4 or period 2 to period 5, the gamma is the same, right? Because the difference between these two is 3 periods ahead, right? Now, when I put gamma, now in my general notation, these two could be different, right? But if I assume that this gamma st is equal to gamma s minus t, then of course both of these are gamma 3, right? And so then they're going to be the same. So if you make this additional assumption that what matters is not, sometimes this is called the index independence assumption, that only what matters is how far ahead you're looking, not from where you're looking, right? Then if you combine this with time consistency, then the only functional form of the discount factor that you can get is this object here. That the discount factor is some delta raised to the power s minus t, right? And this is typically what you have seen in your first year micro courses, right? In your first year micro, what you saw was this gamma st was basically delta to the s minus t. Okay? And so this little two-page exercise also points out that, in though in first year micro, you're just used to just writing the discount rate as some constant delta to the power s minus t. Embedded within that is these two assumptions, right? You're embedding within it time consistency and this assumption here, right? And so what I'm going to hopefully do is show you that, in fact, you can try and design experiments where you can try and test some of these assumptions, or at least versions of these assumptions, okay? So if you assume time consistency and you assume that all that matters is how many periods ahead you're looking, not where you're looking from, then you get to what's called the standard exponential discounting case. And then we go back to kind of standard first year micro, okay? Now suppose that we're willing to assume that what matters is how many periods ahead sort of you're looking at. Like, the only thing that matters is, whether I'm looking 3 periods or 4 periods ahead, not when I'm looking from. Okay, so if I assume this is true, that gamma st is equal to gamma s minus t, but I'm no longer going to assume time consistency, right? In other words, I'm no longer going to assume that these ratios are equal, right? In other words, the ratios can either be either gamma 1 over gamma t can be strictly bigger than gamma naught over gamma t minus 1, or the other way around, okay? Then I'm just going to rearrange this so I get the function, the discount rate as a function of t on the right-hand side, okay? So I get gamma 1 over gamma 0 is either strictly bigger, can either be larger than or smaller than gamma t over gamma t minus 1. And this object on the right, I'm going to call it g over t. And the reason I'm carrying out this exercise is because this literature on time inconsistency characterizes the nature of time inconsistency by looking at this little g function, okay? So it turns out that if this little g function is increasing in t, you get what's called present bias. In other words, agents are biased towards the present in a particular way. They weigh utility towards the present more, okay? On the other hand, if g of t is decreasing in t, the agent has kind of increasing patience. Okay, and this is something that's typically not been addressed in the empirical literature much. Or typically, people usually are much more worried about present bias, and that's just because a lot of kind of data and a lot of introspection suggests that this is actually the relevant issue for most people. They tend to be present biased. Okay. So far, again, we've made we've been pretty general about what this gamma function looks like. When we try to take these kind of models to data, then we have to be a little bit more ad hoc about the forms of these gamma functions, just because we want to do some estimations, and it's hard to estimate these functions totally non-parametrically. So we're going to, so in the literature, there's kind of two primary ways in which people try to parameterize these functions. One is called the hyperbolic discounting case, okay, where this gamma of s is given by 1 over 1 plus alpha s, okay. Or I would say, maybe 95% of the empirical work on time inconsistent preferences uses what's called beta delta preferences, or what's called quasi hyperbolic discounting. And in that case, the gamma of t is assumed to take this particular form. Gamma of t is equal to 1 if t is equal to 0, and it's equal to beta times delta t if t is strictly positive. Okay. So these are two different discount rates, and why we use these discount rates, or why we use these particular parameterizations, I'll get to in the next slide. So first, for the hyperbolic discounting, what does this g of t function look like? This g of t function looks like this, okay? And you can see that it's going to be increasing in t, okay? And for quasi-hyperbolic preferences, the g of t function looks like this. And this is a very simple function, right? In terms of if I was to graph this function as a function of t. So here's t. At t is equal to 0, this function is beta delta, is equal to beta delta. Okay, and we assume that beta lies between 0 and 1, and delta lies between 0 and 1. Okay, so beta delta is going to be some number that lies between 0 and 1. So that's what it's going to be at t is equal to 0. And for any t that's strictly bigger than 0, it's going to be equal to delta. Right? And since beta is strictly between 0 and 1, beta delta is going to be strictly smaller than delta. Okay. And so this g of t function is going to look like this. Okay. So it's in fact increasing, but up till period 1, and then it's basically flat. Okay. So this is what's called quasi-hyperbolic preferences. This function g of t looks like this, okay? And just to anticipate a little bit, the reason why people like this g of t function is that supposing beta was equal to 1, okay, then of course this function would be a straight line, right? And then you would get back the standard exponential discounting function, right? So unlike the hyperbolic discounting case where you cannot nest the standard time-consistent model, in the quasi-hyperbolic preferences case, you can nest the standard model as a special case of the hyperbolic model. And so that's why in empirical work, or at least in my estimation, that's why in empirical work, people prefer to use the quasi-hyperbolic parameterization, because the idea is, look, I can nest the standard exponential case. If I can estimate beta and delta, I can test whether beta is equal to 1. If beta is equal to 1, then I can say, look, these people are basically time consistent. Whereas no matter what value of alpha over here is, this g of t is not necessarily going to be equal to 1. Okay. So just as an aside, so up till now, this was just kind of tied into your first year micro, trying to connect this model to your first year micro. But the real reason why people are interested in these model of time inconsistent preferences is because I'd say, maybe in the past 20 years, there's been a huge increase in the interest in trying to move away from standard neoclassical explanations to explain behavior that's kind of hard to reconcile with the standard model. And people have picked up on time inconsistency as one way to reconcile behavior within the context of an economic model. Okay, so that's really why people have been interested in the kind of models that I've presented before, right? Now, how have people found evidence for this? Now, of course, anecdotally, people have talked a lot about, how people like to procrastinate, or people are present biased in how they make choices. But thinking about kind of the literature kind of starts with thinking about lab-based evidence. So you go to a lab and you have people make some choices, and those choices suggest that they have some kind of present bias. And these kind of lab evidence typically, comes in the following form. At least in the first wave of experiments, people would invite college undergraduates into a lab, and you would ask them, you can either have 10 rupees today or 15 rupees tomorrow. A lot of people would prefer the 10 rupees today. Or you could say, or you could make this choice between having 10 rupees tomorrow and 15 rupees the day after tomorrow. More people would choose to have 15 rupees day after tomorrow. So the idea is, when you're making there's something very special about the present. When you're making a choice in the present, you kind of just want to consume all you can in the present. But even if you shift that forward by a little bit, you're willing to be a bit more patient. So you're willing to wait. If you're making a choice about choosing something between tomorrow and day after tomorrow, you're willing to be patient. But if you're making a choice between today and tomorrow, you're very impatient. You kind of want everything today, right? So that's kind of the nature of, so there was a lot of lab work that suggested that this was true. Typically, what people were choosing between in the initial wave of experiments was over money. People were making choices over money. But there was a lot of criticism of the initial wave of experiments. Some of it had to do with the fact that ultimately money is fungible. As long as people know that there's some external market where they can invest this money, you're not really picking up anything about time preferences. You're just picking up something about the interest rate or people's marginal rate of substitution. And so then people moved away from looking at money to looking at choices over effort directly. Instead of asking you how much money you want today versus tomorrow, I'm going to ask you to carry out some task. And usually these were just kind of silly tasks in a lab, like solve a maze or something. In the example I'm going to use, it's going to be about carrying out vaccination. So you move it away from what's called the money domain into the effort domain. So you address some of the criticisms that came upon then. But in that literature, you do find effects on effort. Yeah.
Does the form of gamma in any way depend on the form of the discrete?
No. So in principle, no. So the gamma here can be defined totally independently of the U.
But shouldn't it depend on the shape?
So should in what sense?
I mean, suppose I'm talking about the group, utility increases as the amount of the group increases.
Right.
Suppose I'm talking about the bag, and in that way, my gamma should not be.
So
Suppose I'm talking about X topic, I will be like the kind of patient in that, like I will defer that in time.
So I think, so your first example to me had to do more with the curvature of U. The second example to me has to do with maybe just gamma itself. right? But it doesn't, so in principle, of course, so I guess maybe the answer is, in theory, there's no relationship between gamma and U. For particular applications, you may want to specify particular forms of gamma because you want to capture some particular way in which people are discounting preferences. That being said, in practice, people only ever use, I mean, in empirical work, I would say 90% of people use kind of this version of time preferences. I think it's an interesting question to ask. It's an open research question, and I'll suggest how we can use existing data to think about what happens if you think about hyperbolic preferences, for example. But in general, yes, I think trying to experiment with different forms of this gamma is a relatively unexplored topic. People haven't really thought about much beyond hyperbolic, quasi-hyperbolic preferences. Okay, so the motivation really for this model comes from kind of anomalies in either lab data or anomalies in kind of real world actions, and people have thought that present bias preferences might be one way to reconcile people's actions with kind of an economic model of decision making. Okay, and so the most common way people have thought about this is through writing down what are called quasi-hyperbolic preferences. So just substituting in that particular form for gamma, the quasi-hyperbolic form for gamma, into my utility function, you get this particular form for utility. Okay, and again, this nests the standard exponential model. If beta is equal to 1, then you get back to the standard exponential model, which I think accounts for this popularity. So, and adding just one additional parameter, adding just this one beta, allows you to capture at least this fundamental insight behind present bias, which is that the present is somehow more valuable than any future point. Okay, and that keeps happening whenever you get to whatever becomes your new present. And just adding one parameter captures this, what you can think of as potentially being fairly complicated behavior, right? And so that's the other reason when we come to empirical work, people like just having these quasi-hyperbolic preferences. So if I was to collect all of the parameters in this model and write them down, it would be the beta, it would be the delta, and it would be the U functions, right? So all of these together are the parameters in the model, right? The beta, the delta, and the U functions. So we're going to, when we sometimes talk about the full model or the full set of parameters in the model, I'm going to refer to that by theta. Okay. So again, we're going to go back to this model where people are choosing to take actions, A sub t, in either period 0, 1, and 2. Okay. And so we've specified, if we go back to standard micro, now I've specified preferences. I should specify a budget constraint. Okay. So here's the budget constraint. The budget constraint is that this agent has to complete V tasks in period 1 and 2 put together. And that agent has to decide how many of the tasks she's going to do in period 1 and how many tasks she's going to do in period 2. Okay, A1 and A2. Now, if R was equal to 1, that would just say the total number of tasks in period 1 and 2 have to sum up to the total number of tasks V that you need to complete in this period. But we're going to add what we call R, which is an interest rate, which is basically a way of saying that one task completed in period 2 is going to count for R tasks overall. So if, for example, R is equal to 1.5, that says any task you complete in period 2 is going to count 1.5 times. Okay, so that means that you have more of an incentive to do more tasks in period 2 because any given task in period 2 is going to count for 50% more than if you did it in period 1. On the other hand, if R is equal to 0.5, then you have an incentive to do more tasks in period 1 because any given task in period 2 is only going to count as half a task overall. Okay, so this is trying to capture the idea of an interest rate. Okay, and as we'll see now in the experimental application, the experimenters actually implemented this. Okay. So what does the model look like here? This is the utility function in any given period little t. And the key point I wanted to make here is that when we think about an agent in period t, okay, and he in period t is thinking about how he's going to perform in period t plus k and period t plus k plus 1, this person sitting in period t thinks that when they're looking at t plus k and t plus k plus 1, the rate at which they're going to discount utility between those two periods is going to be delta, okay? Because it's going to be beta delta t plus k plus 1 divided by beta delta t plus k. So you look at that ratio, all that's going to be left is going to be a delta. On the other hand, when this agent gets to period t plus k, they are going to discount utility by beta delta. okay, because they are now in the present, and in the present you always discount utility from the next period at the rate beta delta. Right? So this is the fundamental time inconsistency, right? When I'm sitting in period 0 and I'm thinking, oh, how am I going to discount utility between period 2 and 1? I'm saying, well, I'm going to discount it by delta. When I get to period 1 and I have to decide how to discount utility between period 1 and 2, I'm actually going to discount it by beta delta. Okay? So that's the fundamental notion of time inconsistency, right? That I behave differently in period 1 than I think I would when I'm thinking from the point of view in period 0. Okay, so the agent is discounting in a time inconsistent manner. Okay, so the next question you can ask is when the agent is maximizing utility, does he understand this inconsistency? Does the agent understand that he's going to behave in this weird way, right? So up till now I've talked about the naive agent. Basically, this agent doesn't understand. When they're solving this model, they think that, oh, I'm present biased in this period, so in this period I'm kind of lazy or I want to consume stuff now, but starting next period I'm going to behave like a perfectly rational agent. So that's a naive agent. So these agents are a little weird in the economic sense because every period they kind of end up being surprised by their present bias. On the other hand, you have these sophisticated agents who kind of are like, look, in this period I'm going to discount utility by beta delta, and I'm going to think that in future periods I'm going to behave, but I know that in fact in the future periods I am also going to misbehave, so to speak. So these agents are called sophisticated agents who kind of understand the time inconsistency, and in fact a lot of the literature depends on agents being sophisticated in some sense. Because if an agent is sophisticated, then they kind of know they have a problem, and then you can kind of design contracts for those kind of agents to solve the problem. So within this literature there's a lot of kind of people try to offer agents products that will tie their hands, what are called commitment products. And these commitment products are really only relevant for people who are kind of sophisticated, who know they have a problem. Naive agents don't think they have a problem, right? So if people don't think they have a problem, it's kind of hard to get them to fix it, whereas sophisticated agents actually understand they have a problem. And then there's sort of agents that are somewhere in the middle. They kind of think they have a problem, but they don't kind of know how bad that particular problem is. Okay, and so this is just writing down, again, going back to your first year micro. In the first period, the agent is just going to choose task allocations to maximize the discounted utility subject to a budget constraint. What do we observe? We observe A1 and A2, the allocation decisions made by the agent in each of the two periods. We also observe the interest rate R, and we also observe the total number of tasks V that the agent has got to carry out. Okay. So one of the things that is true is that if the data was purely observational, then in fact it would be very hard for us to identify all of the parameters, model parameters theta. In fact, even with infinite amounts of data, we wouldn't be able to identify all of these parameters. Okay, so we can then ask what kinds of assumptions do we need in order to identify this model. And so I'm going to talk about, maybe given the time constraints, maybe I'll just talk about one paper, but if I have time, I'll talk about the second one as well. These are both papers that write down very simple dynamic choice models and ask to what extent can we learn anything about these discount rates from taking the model seriously and collecting data that is kind of tailored towards this particular model, right? And this data is going to come from a randomized experiment, and we're going to see how we can use data from this randomized experiment to learn about these time preferences. Yeah?
Sir, I'm not quite able to understand the concept of capital R.
Okay.
You're talking about some experiment in which health agents have to decide, like in this case maybe vaccinating how many households.
Yeah.
Example of R in that context?
Yeah, so for example, R in that context ranges from something like 0.75 to 1.25. So basically you tell this health workers are told, you have to decide. So they're told in period 0 that let's say they're told on Sunday that on Monday and Tuesday you have to decide how many vaccinations to carry out. In total, you have to carry out 300 vaccinations. And R, let's say for an agent, so the simplest case is R is chosen for an agent to be equal to 1. And they're saying, look, you have 300 vaccinations. You have to carry it out between Monday and Tuesday. Tell me how many you're going to do in Monday, how many you're going to do in Tuesday. That's kind of the most standard way to do it. The twist is to tell some of these agents that, so let's say R is equal to, for simplicity, let's say R is equal to 1.5. So this agent is told you have to complete a total of 300 vaccinations. Every vaccination you count in period 1 counts as 1 vaccination, but every vaccination you complete in period 2 counts as 1.5 vaccinations. Okay.
What would be the motivation behind this?
This is purely because we want to identify these time preference parameters. Okay. Now, in the paper, they make the case that this R is going to help them to design better contracts for the agents themselves. So when you read the paper, you can decide for yourself how convincing that is. But in the context of the model, they try to set this R because they want to help identify this delta. Okay. I do think that one of the problems with, so this paper has not been published now for 4 or 5 years. I think one of the problems they do have with referees is referees not understanding, not being convinced that this R is really a relevant policy parameter, right? They would say, look, in any given health department, no health department is going to tell the health worker, one vaccination counts as 1.5 if you do it on Tuesday instead of Monday. So I do agree that in terms of realism, this paper has a problem. Here I'm using this more as kind of a conceptual, as a kind of a proof of concept of trying to use an experiment to answer, to identify a structural model. Yeah.
Could be relevant in the case there's some kind of outbreak, and if you vaccinate today, then there will be fewer diseases tomorrow.
Right. So that's true. Yeah, so you could have a world in which you set R equal to 0, for example, right? That would be the extreme case, which would just say, like, you have to do all your vaccinations in one day because by Tuesday it's going to be too late. Yeah, that's right. So R being less than 1 is you want people to do as quickly as possible. Yeah, so I agree with you. So in fact, R being equal to less than 1 is what you might imagine as being at least somewhat relevant for a health department. In their paper, actually, they assume that the policymaker wants health workers to smooth over time, which is kind of the opposite of your comment, which is that they want to set A1 and A2 roughly equal to each other. And that's not clear why that should be the case, right? Maybe, because maybe you want people to go out every day and go to the villages and not just go on one day or something like that. But it's not necessarily compelling, yeah. 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 Oh, sorry.
So basically, if you consider something like people learn on the job, so even if they decide that they will do say 150, 150 on 2 days,
Yeah.
on the first day they are still in that learning phase and they complete say 100 or 125, and then on the second day they get more sophisticated at their own work. So even if what they have decided or what was suggested to them that it will be like 1.5 times or 1.5 times, it is more like it is learning by doing or some kind of.
Yeah, so I think that would be a big problem for this paper if that were true, because then you would actually have to account for the fact that your choice of A1 implicitly affects some learning, because you might say, look, I only want to do 50 because I'll see how I learn and then I'll do more on the next day. So, so that they actually address in the paper because they work specifically with health workers who have been doing this for a long time. So these are people who kind of know the villages they have to go to. They have been vaccinating on average for, I think maybe it was a couple of years before the project started. So they kind of eliminate learning as a potential reason for doing this. In the second example that I'm going to give you, if I get to it, something similar is an issue. There kind of people are trying to decide whether to retreat a net or not. And there you might worry about the fact that people are learning about if the net is useful, then they'll retreat it. If it's not useful, they won't retreat it. But ex ante, they may not know if it's useful or not. So there might be a learning reason for doing this. So in these models of time inconsistency, typically learning is excluded as a particular cause. And that's why the kind of context people work on is one where kind of learning is not important. Not to say that learning isn't important, but for these models, they try and find a context where it's not important. Yeah, sorry, yeah. This model is about effort, yes. There is. So that comes in that's the U. Yeah. Mm-hmm. Yeah. Uh-huh.
This R is basically changing the utility from the periods.
Yeah.
And that utility will also change because of my discount rate.
Yes, so everything that you've said should be in the first order conditions, right? The first order conditions is going to tell you exactly how you're going to trade off marginal utility in periods 1 and 2 as a function of the discount rate and a function of R, right? So that first order condition is actually going to be the core of that paper, estimating that first order condition. So they're going to exactly they recognize exactly the fact that if you assume agents are maximizing utility, then the choice of A1 and A2 is going to reflect the marginal utility in period 1, the marginal utility in period 2, and the beta delta, and the R. So it's actually going to be part of the estimation. Yeah, I think there was another question. Yeah. Is it disincentivizing present bias?
In the sense of saying that you get to the because in case of effort, but in case of the filling it then in the last amount you get
Oh, yeah.
present bias, I still go with the 10.
Yes.
Is this assuming that the 9?
Yes, so you're right in that you can think of particular choices of R, like really high choices, like if you set R equal to 0, for example, then yeah, that's definitely forcing everyone to do everything in period 1. So you can think of this as counteracting people's tendencies towards postponing effort into the future. So the lower R is, the more likely you are to try to push things towards period 1. And so variations, and so in fact, this variation in R is going to kind of, if you assume people have different rates of time preferences, so different people have different bias, different rates of present bias, then this variation in R is going to affect different people differently, but exactly in the direction that you suggest, right? It's going to push some people towards doing more today, given holding constant their present bias. Okay, so let's see where were we? So we've gone past this. Okay, so let's see. Let me skip this because this was actually a little bit more general than the paper I want to talk about. Essentially here I was saying that while I'm going to do this particular paper that tries to show you how to use structural models and randomized experiments together, there are other papers that also do it. And this is this paper by Athanasio, which uses a randomized experiment from Progressa to estimate a structural model. In pretty much, I mean, it doesn't talk about time preferences, but it does it in a similar flavor to the paper I'm going to talk about, in the sense that they use the entire experimental data. And then this point I wanted to make here was that there's actually a completely different way in which people use experiments and structural models, and that is this paper by Todd and Wolpin. In what they basically do here is they use the control group to estimate the data, to estimate the model. They only use control group data to estimate the model, and then they check their model by using the treatment group data. So basically what they do is they estimate a model of fertility and schooling using just the control group data, so no experimental variation at all. And then they say, well, I'm going to check how good my model is by checking to see how well it predicts the outcomes in the treatment group. And so then they use the treatment group data to predict the outcomes, and then they compare the treatment group outcomes to the predicted outcomes. So this really is, if you like, just using an experiment as a validation exercise, not for anything else. Okay, and so this is, this is actually the, I think probably, I think maybe there's one other paper that does this, but this you can think of as kind of another use of at least to date, another use of experimental data in the context of a structural model. So let me skip this because I don't think we have enough time. So let's go back to this paper here. Okay, so essentially this is the setup, which is what I've introduced earlier. The only additional piece of information I'll add here is that it has been well known that if you just have observational data, typically you cannot identify time preferences. So if you look at all these applied papers that use dynamic discrete choice models in industrial organization, they will typically, firstly they'll use time inconsistency, and secondly they'll typically say, look, I set delta equal to 0.95, and then I'm going to estimate the U function. And that's, all of that comes from this Rust paper that shows that in general, you can't identify both the delta and the U with typical observational data. So how do Andreoni and get around this? Andreoni et al. Get around this by collecting better data. So they ran a randomized controlled trial to collect data that is typically not, that has sources of variation that aren't found in observational data. And then they also place stronger assumptions on the preferences themselves. So what's the actual application? So as I talked before, this is an application to Pakistani health workers who have to allocate vaccinations over 2 time periods, and they have a target vaccination rate of V. This interest rate R is varied by the experimenters, so they had to go in, work with the health department to get them to agree to do this kind of, in some sense, crazy sounding experiment. And the way in which they are going to be able to identify these time preferences is that for I think about half of the agents, the health workers, they are called in period 0
to make their allocation decisions about period 1 and period 2. That's called the advanced choice. So I call you in on Sunday and I ask you to make this decision about how much work you're going to do on Monday and Tuesday. Whereas for the other set of people, when they come in on Monday, they have to make their choice about how much to work on Monday and Tuesday. So that's called the immediate choice, and that's called the advanced choice. Okay? And you can see how this maps into kind of, in period 0, I have to predict how I'm going to behave in period 1 and 2, whereas in period 1, I have to decide now how much to work today and how much to work tomorrow. So this is going to be very important because it's going to allow us to identify different time preferences for these two different groups. For the people who have to make the immediate choice, I'm going to identify beta times delta because I'm deciding today between how much work to do today and tomorrow. The discount rate between today and tomorrow is always beta delta. On the other hand, for the people who are deciding in period 0 how much to work between period 1 and period 2, that comparison is only going to involve delta. It's not going to involve beta. So from these guys, I'm going to just get a delta. From these guys, I'm going to get a beta delta. Okay, so we're just going to write down the agent's utility maximization problem. So here's the agent's going to maximize utility over 2 periods. Gamma 1 and gamma 2 are the 2 discount rates. And this is the budget constraint, right? This is the point that someone was making, that look, if you write down this optimization problem, you're going to get a first order condition that is going to have the marginal rate of substitution as a function of the discount rates and the interest rate, right? This is a standard Euler equation. In fact, the marginal rate of substitution is going to be equal to this function of the discount rate and the interest rate. Okay, so this is going to be, if we assume this is how people are going to behave, the first order conditions should, the values of A1, A2, and R should satisfy this equation. And then I'm just going to combine the first order condition for both agents who make the choice in advance as well as for the agents that make the choice immediately. All that changes is the relative discount rates, right? So for these are agents who are making the choice immediately, I get the ratio gamma 1 over gamma 0. For agents who are making the choice in advance, I get gamma 2 over gamma 1, right? So that's the only difference. Again, I can look at the first order conditions. I can take logs here. Taking logs, I get this object here, okay? And I'm taking logs here because later on I'm going to try and estimate some objects using linear regression. Taking logs kind of linearizes this problem. And so what do we observe? So we've gotten what we think is some kind of estimating equation. We still have to think a little bit more about that. What do we observe? We observe individuals' allocation decision. We observe D and R. Both D and R are assigned by the experimenter. They decide whether someone makes the decision early, immediately, or in advance. They decide the interest rate. So these are experimentally assigned. A1, A2 are chosen by the health worker, but we observe all of these. Okay, and so for each agent, we have their discount rates and we have the utility function. So for each agent, we have a parameter theta I that kind of parameterizes their decision problem. And so our question is going to be, what can we learn about theta I from this data, A1, A2, D, and R? Okay, so all I'm going to do here first is just rewrite this equation, taking the log of R to the left-hand side. Okay. And we can look at this object here and we can say, okay, supposing we knew the utility function. So supposing U was known for each individual, okay, then the left-hand side, and R is known because R is assigned by the experimenter, then I would know the left-hand side for each person, right? And since I knew the left-hand side, I could infer, therefore, I knew the right-hand side for each person. I would either, for each person I would, if a person was in the advanced group, I would be able to compute gamma 2 over gamma 1. If a person was in the immediate group, I would know their gamma 1 over gamma 0, right? So if the utility functions were known, life would be really straightforward. I could directly learn about the individual specific time preferences. So this is actually kind of important for this paper because what they're going to be interested in is the individual level time preferences. And this is the first step towards figuring out how they might learn about those. Because we know if the utility functions were known, we could directly recover these individual specific preferences. Okay, and this is exactly what the paper does. It assumes that the utility function for every agent is actually the disutility of effort. That's why you have the minus sign, and it's a quadratic. Okay, so you just have a disutility of effort, which is convex in the number of tasks you have to carry out, and it's the same for everyone. For everyone has this quadratic utility function. Okay, and we can talk about how we might want to relax this later on. So everyone has this quadratic utility function. But if I assume agents have this quadratic utility function, then the left-hand side is going to be known for everyone. And therefore, I can find out what the gamma 1 over gamma 0 or the gamma 2 over gamma 1 is for every single person. So that's exactly what they do. If you assume utility functions are quadratic, the left-hand side, in fact, becomes equal to, you can show that this ratio, A1 over A2 times R, okay, this is equal to either gamma 2 over gamma 1 for the people who make the decision in advance, and for the people who make the decision immediately, it's equal to gamma 1 over gamma 0. If I assume beta delta preferences, gamma 1 over gamma 0 would be equal to beta delta, and gamma 2 over gamma 1 would be equal to delta. Okay? So in this simple view of the world, I can directly, for each person, figure out either their delta or their beta delta, depending on which group they were assigned to. Okay? So this just says that we can just only figure out one of those ratios. Okay? So supposing, so that's what the paper does. Okay? Now, we can in fact go further than the paper. So supposing that we assume that the agents are hyperbolic. Okay? So supposing we assume that this gamma t function is equal to 1 over 1 plus alpha t, and this alpha is different for each person, then as long as agents have quadratic utility, you can show that in fact the alpha is equal to this object over here. Okay? And so that, in fact, you can then recover the entire discount function gamma ti. Okay? Because you've discovered alpha. Okay? So this is just a way of saying that you can use the data they have, and you can actually go a little bit further and even test whether agents have hyperbolic preferences. Okay, so that's sort of a little bit of an aside, but also sort of a, one value to kind of reading these papers carefully is you realize that in fact you can sometimes do more with the data than what the authors have done themselves. Okay. Now this just says that if agents have hyperbolic preferences, this ratio is, as I said earlier, either equal to delta for the people who make the advanced decision, or it's equal to beta delta for the people who make the immediate decision, right? The main point, though, is that for each person I, we can identify delta or beta delta, okay? So this is what the results look like. So this is the discount factor. This is for the people who make the advanced choices. This is for people who make the immediate choices. And in fact, so this is something that, again, is something that if you start collecting your own data, you'll quickly realize that there are a bunch of people who just behave like completely crazily in all your experiments. They do stuff that makes no sense. And it's always an issue of how you deal with people who do things that make no sense. The usual practice is to exclude them. So they've excluded, I'm not sure now, I think maybe it's 10 to 15% of the data. It's safe to assume that in any experiment you run like this, 10 to 15% of your sample just behaves in a totally crazy way. And so either you can take that very seriously and you can figure out how to deal with them, or you can just exclude them, which is what most work tends to do, is just exclude them because it's kind of hard to think about how they're behaving. Maybe they just don't understand the experimenter's instructions. They just don't know what, they don't know what the instructions mean, or they're just, trying to do something as quickly as possible, and so they make answers that make no sense. So that's usually, I think, the assumptions under which these outliers are excluded. So this is just a histogram of what the discount rates look like. And the main point for showing you the graph is that typically if you look at the discount rates for the immediate choice, they're typically lower than those for the d is equal to 0 choices, so the choices that are made in advance. And that's consistent with this literature that says that there is present bias, that people are kind of discounting the future more when they're in the present than if they are taking the same decision from some kind of an ex ante perspective. So these are some of the people who behave crazily, right? So these are people who if you take their responses seriously, would have values of delta and beta that are strictly bigger than 1, that are actually telling you that they're not discounting utility back. They're in fact, discounting it. They are forward-looking agents, if you like. I mean, they're sort of forward-biased agents, if you like. And so these authors just drop these. They just drop these outliers. Okay. And so the next question is going to be sort of thinking about how, once we've recovered these parameters, what can we use them for, right? So you've discovered these parameters. You found, some people have, for some people you found delta, for some people you found beta delta, but you don't quite. So that's well and good. What else can you do with them? So that's kind of the first question I'm going to address. But before I address that, there's something else that I think is useful to point out. And in fact, the latest version of the paper, which I was just looking over yesterday, takes this much more seriously, which is that if you think, as usual with these kind of, one of the problems with an experiment like this is you're kind of trying to estimate a very well-defined utility parameter, but you're trying to do it not in a lab where you can control everything very tightly. You're trying to do it out in the world with the health department, with health workers and stuff, and you don't always know how well the stuff is going to go when you're trying to do something out in the field. So now usually what happens in the lab is, what happens when in this setting is you want people to actually carry out the allocation that they say they're going to do, right? If a health worker on Sunday says that she's going to carry out, 100 vaccinations on Monday and 200 on Tuesday, you want her to somehow actually follow through on that. In the lab, the way this is typically carried out is by giving them a huge bonus if both of these targets are met. So if I was doing this in the lab, I would tell the student, if you meet these targets in the lab, if I could somehow reproduce in this lab, I'll give you 10 times the minimum wage. And usually in the lab, you can design incentives to be high enough so you get 100% compliance. So you don't have to worry about people who say they're going to do 100 vaccinations but only end up doing 50. The problem was here that even though they tried to do something like this, so what the workers were told was that if you complete the allocations on Monday and Tuesday that you told us you were going to do, you'll get 1,000 rupees bonus. And the daily wage for these workers is something like 100 rupees. So this is 10 times their daily wage, more or less. Only about 50% of the workers actually completed the task that they said they were going to complete. Okay? So this is, in principle, a pretty big problem for the experiment itself, because now you have to take into account the fact that maybe some people knew that they weren't going to complete the tasks, and that affected how they chose A1 and A2, and none of that is modeled in what I've done so far, right? Here, there's nothing that captures this idea that maybe I say I'm going to do A1, but I'm not going to do A1, right? So that's kind of a problem with the paper. I'm going to ignore this for now because it kind of takes away from the main point I'm going to make. So for what I'm going to do next, I'm going to kind of assume that they implemented the experiment in a way that almost everyone, or 90% of the people, did exactly what they were going to do. But if you read the paper, this issue actually takes up a fair amount of space. So what they're going to do is, they have these time preference parameters, and they want to somehow validate them in some way. They want to say, okay, what sense do these parameters make? Are they even useful for us to have estimated? And the way that they decide to make use of these parameters is to say that we are going to use these deltas and these beta deltas to design a contract for these health workers. And what we're going to try and show you is that under this design contract, the health workers behave in a way that we predict they would behave. And that is kind of a validation of these delta and betas, because if the delta and betas were just complete noise, then our predictions wouldn't hold, and then you would just think of you've estimated just garbage. So in my view, that's kind of the main reason to do the second part of this paper. The secondary reason is a kind of a proof of concept. They can say, look, if you as a policymaker are interested in designing a contract, and this contract depends on the preferences of the health workers, knowing the preferences of the health workers can help you design a better contract. Now, as people have already pointed out, maybe this is not such a realistic context in which this should apply, but think of this as more like a proof of concept rather than something that an actual health department would want to do. So what do they do here? Basically what they do is they design a second experimental drive where they offer each health worker again a choice between taking actions in period 1 and period 2. So they come back 2 weeks later, they're told, okay, here's another set of vaccinations you have to carry out on Monday and Tuesday, but now the interest rate that they're given, RI, is a function of the choices they made the first time around. So that's why I'm denoting it by an RI star, and this RI star is a function of the elicited delta and beta delta from the first period. And in fact, it's elicited exactly in a way assuming quadratic utility. And they call these contracts tailored contracts because they're tailored to each person as a function of her choice in the first period. Okay, all of which is captured in this RI star. Okay, and then they ask, okay, how should we choose this RI star for each person? And they say, well, in order to figure that out, we need to maybe think about what objective function the policymaker should care about. And so what they argue is that the policymaker cares about smoothness of performance rather than total performance. So they assume that the policymaker wants to maximize a Leontief production function. So essentially what they want to do is have equal number of vaccinations on both days. As people have pointed out, maybe this is not reasonable. Maybe what you want to do is maximize the number of vaccinations on day one, right? You could think of some reason why they might want to maximize, why they want this production function. Maybe they want health workers to be out in the village every day so that people see them, etc., because maybe the health workers can do other things than just give vaccinations. But this is kind of relatively ad hoc. So they ask about, okay, let's think about the principal-agent problem. Now the principal wants to choose the contract. The contract term is now just this choice of R. They want to choose the R to maximize this production function, subject to the constraints that the actions that the agent health workers are going to be chosen are themselves going to be the object, the outcome of some maximization exercise, right? So I'm going to choose how to maximize my production function or my policy function, knowing that the health worker is going to maximize her utility subject to this budget constraint, right? So I can write down this joint maximization problem, and that's going to give me an optimal choice of Ri, okay? And so they say, and so this, in fact, you can solve it fairly straightforwardly. You can, in this problem, for this particular agent, what the principal would like is for A1 to be equal to A2, right? Because that's sort of what is going to maximize their production function here, right? A1 is only going to be equal to A2 if the interest rate Ri is equal to beta times delta. So, right, so beta times delta for the people who make the immediate choice, and just equal to delta for the people who make the advanced choice, right? And so this tells us how the principal is going to choose the optimal policy. The optimal policy is going to be equal to beta delta for those people who made the immediate choice, and it's going to be equal to delta for the people who made the advanced choice, okay? So in order to validate this, they need to have some kind of control group as well. So half of the health workers were given the contract that depended on their beta and beta delta from the first drive, whereas the other half were just given a randomly chosen interest rate between 0.75 and 1.5. So this will allow them to benchmark how well this tailored contract does relative to an untailored contract, okay? And in the second drive, the other thing to point out is that exactly the same immediate and advanced allocations were used as in the first period. So if you were immediate in the first period, you're also immediate in the second drive. And if you were advanced in the first drive, you're also an advanced in the second drive. Okay. So this is just a graph that shows you that the randomization went as expected. On the x-axis, you have the elicited drive 1 discount factor, either delta or beta delta for each person, right? And on the y-axis, you have the interest rate that was chosen for you in the second drive. This just verifies the fact that for the people who received the untailored contract, the interest rates were just randomly allocated between 0.75 and 1.5. They were just chosen randomly. It didn't depend on what their first period interest rate discount period was. Whereas for everyone who was in the tailored group, their second period their drive 2 interest rate was the same as their drive 1 discount factor. That's just the 45-degree line. Whatever your discount factor was in the first period, in the first drive, I use that to set your interest rate in the second drive, right? So this is just capturing that, okay? Now this is the outcomes. So this is the number of vaccinations that you made in the second day, and this is the number of vaccinations you made in the first day in drive 2, right? Now remember, the objective function of the principal is to have everything lie essentially on the 45-degree line, because that says you're doing as many vaccinations on the first day as you're doing on the second day. And we're comparing the tailored group to the untailored group, okay? And it's not, this is a little bit in the eye of the beholder, right? But their argument is that the second graph is more clustered around the 45-degree line than the first graph, right? And so, this is the eyeball metric, which you can sort of take in any way you like. To me, it's sort of, there is some suggestive evidence that this is true, but they can also then look at it using a regression format. And so what's the dependent variable here? The dependent variable is how close you are to performing the same number of tasks in both periods, right? If V1 is equal to V2, the dependent variable is 0, right? Otherwise, it's strictly greater than 0. So they regress how close you are to equality, how close you are to the 45, to doing the same number of tasks in each period, and they regress it on whether or not you received a tailored contract, okay? And there's, as you might expect from the graph, there is a negative effect here. So if you received a tailored contract, in other words, if in the second drive your R was a function of your first period discount rates, you are more likely to actually allocate things equally relative to people who are just given a randomly assigned interest rate. Okay? So that's kind of what the first 3 columns show you. The second set of 3 columns try to break it down by whether it's the tailoring matters more for the people who were in the advanced category, in other words, for the people from whom we elicited their delta, or did tailoring matter more for the people who were in the immediate group, which is for people who we elicited the beta delta. And here there's some evidence that really what the effect is really coming from people who were in the immediate category. In other words, for people who we assume the beta delta. That really it's for these people for whom the present bias is more of a problem that the tailoring actually helped. Okay. So it's not totally clear why this should be true, why it should be the case, except to the extent that maybe these are the people for whom we elicited beta deltas, and using that to inform their R's actually led these people to behave in a way that was more consistent, I guess, with their preferences. So that's sort of you can view this sort of, so I view this graph primarily as kind of I view this table primarily as kind of a validation that the beta and the beta delta that they elicited in the first drive weren't complete garbage. They actually do have some predictive value for how these people behave in the future. And this is actually a pretty, in my view, this is a pretty nice test for how useful these structural parameters are, right? Because in this case, you can actually point to a table and say, look, I estimated these structural parameters in an initial wave. I used those estimated structural parameters, and I was actually able to get people to behave differently as a function of those structural parameters. These structural parameters actually did inform real-life effort tasks in subsequent action. So at least across these 2 weeks when the drive was carried out, these parameters did seem to have some kind of predictive value. Yeah.
So I don't get the dependent variable.
The dependent variable.
Policymakers' objective to maximize the number of tasks rather than remain close to the 45 daily max.
No, so the policymakers' objective function here is the ONTF, right? So if it was what you're saying, then you would use A1 plus A2 or something like that as the objective function. Yeah, absolutely. So that's true. So the other way, and in the paper, the way they try and sell this paper, the way they try and sell this table is to also say that this tells us that in fact the policymaker is also achieving their desired objective, that they have tasks that are more smoothly assigned over time. But that's only true if you believe the policymaker had this kind of Leontief function, right? So to the extent that the policymaker has a Leontief function, then this table also provides evidence for that. To the extent that they don't have Leontief function, this is not a policy relevant table. But this is a table that does tell us that the structural parameters are at least useful in predicting subsequent performance. Okay. So how do I want to summarize this paper? So basically, I think that the way to think about this paper is really kind of the very first, like, super ambitious attempt at trying to estimate structural parameters using an experiment, and then trying to use those structural parameters to do something else. And I think this is kind of an exciting area because I think there's very little done here. I also think that this is an area where you can find relatively small problems and try and tackle them. So you don't need millions of dollars to run some huge experiment. I also think that the one drawback of this paper is, not drawback, but the one thing about this paper that's hard is that they did it in a realistic field setting, right? They went to the health department, they tried to get these health workers to do something like this. But you could try and replicate aspects of this in the lab, right? So you could try and do this in collaboration with psychologists, just get a bunch of students from DU to come in and solve some kind of task problem. And I think that has a lot of value. One, I think 99% of all lab experiments are done on like US undergraduates, and that's just a very narrow population, right? So any kind of work that introduces us to different populations, I think is kind of an independent interest, even if it's just DU undergrads. In Kenya, for example, there's a behavioral economics lab being run by Johannes Haushofer, who basically runs a lab in that gets people to participate in lab experiments, but the people who participate in them are actually not students from Nairobi. They're actually people who live in the nearby slums of the lab, and they come in and they take part in experiments that are all about time preferences or whatever people care about. But it's a very different population, and it turns out that often the results are quite interesting, and just doing it on a different population is kind of interest. So that's the other reason to present this paper. It's just to sort of give you a sense of like, if you are willing to kind of design things super carefully, there is interest in doing these, even I think in kind of a lab setting. And doing lab stuff is much cheaper than doing an actual field experiment, right? Doing a lab stuff, you know, you just need to pay the participants something, but you can stay in Delhi, you can do it in Delhi, you can, you know, you don't need kind of the huge grants and all of that other stuff that you would need to run an experiment like this. And then the other thing to point out is that this is, you know, this is very fundamental stuff, right? This is a time preference parameter that you learned in your first year micro and macro, and it just tells you how little we know in practice about what's a reasonable value for this, how can we even elicit them in a way that doesn't confound it with other things that confound it with the choices that people are making. And just making progress on this, I think, would be super interesting. At the same time, it points out that it's kind of hard to do so without putting a lot of structure on the problem, right? They assume quadratic utility, they assume this two-period problem, right? But it's still, I think the paper is interesting. So another way to say that is that you can start with a very simple model, you know, just a simple model like this, but taking this to the data in a serious way is actually still a contribution, right? So you shouldn't think that you have to write down a really complicated model and take that to the data. You can write down a super simple model and take it to the data as long as it tells us something interesting about these fundamentals. I think people would still be interested. So I think that's the other point I wanted to make with this paper. Okay, here I was going to go back to this log specification that I talked about briefly and think about how one might think about estimating this function just using kind of econometric methods. And so here I just talk about a few modern econometric methods that you could use to identify and estimate models that look like this without making assumptions on the utility function. So in other words, if you think about what we did earlier, we assumed throughout that utility was quadratic, right? So we assumed it was minus a squared, but who knows if utility is minus a squared for these guys? It could be something else. This approach here tries to not make any assumptions on utility. It says utility is just something, we don't know what it is as long as it's some continuous function. What can we learn if we don't make any assumptions about utility? And so this is kind of a set of approaches that we could try to use in a model where we don't want to make assumptions about utility. The problem is that the equation looks something like this. So it's g of, so remember we observe a1, x, and a2. So the equation looks like GA1 is equal to xi tau plus h of a2. Now, of course, if h was linear, then this would be kind of a linear regression problem, and the only problem would be that a2 is endogenous, so you would have to think about some way to address that. Here the problem is that g and h are both unknown because we don't know the u function. So then the question is, how do you deal with estimating tau in a model where both g and h are unknown? And there are some approaches that I talk about in specifically this Ian Chen paper that tries to do some of this. But really, the fundamental problem in doing this extension is that this A2 is endogenous. And so even if this H was linear, you couldn't just run OLS because A2 is endogenous, right? And so what this suggests is that supposing you were to go back to the drawing board and try to design an experiment where you did not want to assume that utility was quadratic, you didn't want to make any assumption that utility was quadratic, you would then need to get an instrument for A2, right? So that means that when you design this experiment, you would need to assign some people a shock to their A2 choice, right? Supposing no matter what A2 is, you tell someone, okay, you told me that A2 is 80, I'll give you an additional 200 rupees if you actually complete the task that you say you were going to complete in period 2. Then being assigned to that group would be an instrument for A2, right? Now, once you have that, then you could come back here and use that as an instrument and estimate tau without making assumptions about U1 and U2, right? So this points out that if you really want to take seriously this idea that you want to relax what the utility function is, you have to go and redesign the experiment, right? So it's another way of saying that there's a lot of value in writing down exactly what you want to identify before you design the experiment. In their context, Charlie and his co-authors kind of they were fine with assuming utility is quadratic. That was not a big deal for them. They're primarily behavioralists, and they're okay with that. But if you really, say you want to do an extension, you could say, well, I want to not assume that utility is quadratic, but then I need to get an instrument for A2. But since I have so much control, especially in the lab, over how people choose A2, maybe I can think of a lever that's going to move people's A2, and then I can have an instrument for A2. And the advantage of that is then I can no longer I no longer need to make assumptions about what U1 and U2 are. Those can just come to me. Those can just be unknown, because this paper by I and Chen is precisely for this kind of model, as long as you have an instrument for A2. Okay, so that's kind of this is just really a potential extension towards future work. This is again another potential extension where we talk about, let's assume that you have CRRA preferences. So people have constant relative risk aversion preferences. If you assume that's the case, then what can you estimate and what can't you estimate? So that's again kind of future work. This is, let's skip this. This is the beta delta results. I think I don't have much to say here except that these are similar to what people found in the literature. This is again directions for future work. So the only thing to point out here is one of the things that I think should become more popular in structural work is something that I think is very common in machine learning. So machine learning is this other area of statistics that's very popular now. Machine learning is largely used for prediction exercises, usually not used for structural estimation. But the one thing that's very valuable, I think, as an insight from machine learning is that they typically, they have a sample, they'll divide their sample in such a way that one part of the sample is going to be called a holdout sample. And that's a sample they will not use for any estimation. That's going to be used completely just to test how well the model fits. So they will estimate the model on what's called the training data, and they will pick the best model they can possibly get from the training data. And to test how well the model will actually work, they test it on the holdout sample. Okay? So I think that kind of logic is actually useful in structural models as well. So Todd and Wolpin do a little bit of that by saying, look, I'm not going to look at my treatment group at all. I'm going to estimate my model in the control group, and I'm going to tell you how good my model is by looking at its fit when I estimate it to predict the treatment group. So something like this can, I think, be done, can be taken more seriously in this approach here. You can hold out part of your sample, and you can test the predictions on the held out sample. That gives you some sense of how well your structural model is doing also. So that's another way to think about extending the work that's out there before. Okay, so this is a paper that I have that I've been writing for a long time now, and it just keeps getting longer. It's also a paper about estimating beta delta preferences in the context of a dynamic discrete choice model and in the context of running a randomized experiment. The way that it's different from the previous paper is that the way I get identification in this paper is we assume that we relax the rational expectation assumption. So this is a paper, unlike the previous model where there was no uncertainty, this is a model where there is uncertainty. So I have an expectation operator here. Typically in dynamic discrete choice models, people assume rational expectations to compute this expectation. Here what we do in our studies, we actually elicit expectations from people, and we use those expectations to solve the dynamic choice program. And it turns out that using elicited expectations gives you an extra degree of freedom, because now you have additional data, and that allows you to identify the beta and the delta. So just kind of the 5-minute reason for why I wanted to introduce this to you was to also say that if you can go out and collect your own data, then collecting additional kinds of data, and in this case, collecting data on beliefs, also helps you identify structural models, right? And in particular, structural models that could not be identified using kind of standard observational data. So again, beliefs are something that are not, of course, how good the beliefs are is a separate question, and I don't think the beliefs in our data set were that great, but methods have improved over the past 10 years. And so to the extent that you can collect good information on beliefs, that's again another source of variation that you can use to identify structural models that typically in the past just kind of assumed rational expectations. And again, this is something that you can do in the lab as well. It's relatively cheap. Collecting people's elicited beliefs about their expected future behavior, for example, is something that's relatively cheap to do. Doing it in a way that gives you something that's not noise is maybe difficult, but at least in principle, it's at least cheap. Okay, so that's kind of all I want to. I guess I didn't get to what I mostly talked. Let's see. I guess I have an overall summary slide. So if there's one main takeaway I wanted you to take was that I think there's value to going back to your first year courses and sort of thinking about these models and trying to take them to the data and asking kind of what kind of data would I need to identify this model, and is there a way that I can design a lab experiment or something very simple that will allow me to identify this fairly simple model, but that's still kind of important because often we don't know even kind of so we don't really have a good handle on what people's time preferences look like. We don't have a good handle on what people's risk preferences look like. So even eliciting those in a clever way using lab experiments would be super interesting. Okay.